Yeah, everybody, welcome. We'll begin with the first talk with Jim Deng, please.
Shall I start?
Yep.
Okay. So many thanks for Fatim and Claudia for the invitation. And it's for quite a while I haven't practiced my poor English. So hopefully it, my English is understandable. So today I will talk about this our recent study on this 3D forming harbor model. And the numerical works are on these three archive papers. And we are also working with this experimental guy with this cold atom experiments, and which was published this year. So I will, in this talk, I will assume actually in this workshop that everyone knows Fermi-Haber model. I will not really go to introduce a lot. And then I will mainly discuss about our numerical result for 3D half-filling, and actually is about mostly about crossover physics above these anti-ferromagnetic phase transitions. We also did some simulations try to compare with the cold atom experiments and also slightly away from half-filling, but I don't think I have time, so I can stop anytime when my time use up. So this is the Hamiltonian Fermi-Haber model. So as I said, I will not really introduce because I assume everyone knows about it in this workshop. And in this talk, I will focus on at the half-filling. That means the chemical potential is equal to 0 in this form, and also on this simple cubic lattice. And our method, the motivation actually is twofold. One is that we would like to have this quantitative and precise determination of these near temperatures for these phase transitions, and also try to improve the understanding in this high temperature above this Tn, which is about crossover physics. There's no phase transition at all. And the second motivation actually is we are working with the experimental guys, and now they are able to realize this 3D Fermi-Haber model on a very large and nearly uniform optical lattice. And they also can successfully lower the temperature and really observe these near phase transitions. For numerical, the method we using is simply this auxiliary field quantum Monte Carlo, or it is also called determinmental quantum Monte Carlo, DQMC. But we do improve this efficiency a little bit by applying a few tricks like fast Fourier transform, delayed update, this tau9 global update, etc. Now we can achieve this system size up to 20 times 20 times 20 with, I would say, quite modest computer time. If we really spend a lot of computing time, maybe we can go to 24 times 24 times 24. Of course, not to very large U or interaction or very, very low temperature. Just say near the phase transitions. Now I'm going to present this Monte Carlo result at half-filling. First, that we are going to determine this near transition temperature. And we know that for this 3D Haber model at half-filling, if we decrease the temperature, we are going to undergo this continuous phase transitions, which is in the 3D Heisenberg universality class. For small u, this anti-ferromagnetic phase transition is arise from the spin wave instability, and the Fermi surface physics here is very important. At large U, then the super exchange becomes important. Then basically in this regime, in that U regime, one can map onto the Heisenberg model. There are already a lot of studies for these phase transitions before by Monte Carlo, by the DCA, by DMFT, dual fermion, the gamma A, etc. And for DQMC, for Monte Carlo study, actually we have the difficulties also in this large U regime because of this. We can have the instability in this density in this matrix, and we can also have got us for weak interaction. We also have problem. For weak interaction, the problem arises from the very severe finite size effects, because now the physics comes from the Fermi surface. If we have small lattice, then we actually can have very few lattice size, which are kind of sitting only, very few points sitting around the Fermi surface. So in these cases, that even if we do this, for instance, square magnetization, and this kind of times this L to the power 1 plus eta. Eta is the enormous magnetic exponent. We can even have the dimonotonic function as system size increase. So here we just apply this so-called twist the average boundary condition. That means for periodic boundary condition, we twist the boundary a little bit and make several twists and then take the average to minimize or to suppress this finite size effect. And then we just apply the standard finite size analysis to determine these phase boundaries. And here we have to say that actually when we use this critical exponent, we simply take from the value which is determined by this classical Monte Carlo for 3D Heisenberg model. So this is our result. So we are able to, for instance, for small u, to determine this interaction with quite good precision, which now agree with the very recent diagrammatic Monte Carlo result. And for all this interaction between 4 and 12, the error bar is in third decimal place. One message here is that around u equal to 8, the temperature, the phase transition temperature, reached the highest point. Before, I think it was argued around 9 or even 10, something there, some kind of debate. Then we move to this high temperature physics above these near temperatures. A simple analysis, we know that at this high temperature regime, that if for small u, then the system will be in the Fermi liquid regime, which we call metal. For large u, then the interaction will prevent a single lattice size is occupied by two sides. So basically, then it will become the system will become, on average, that one side has one and only one atom. In a sense, is in the motor insulating state. Note that we do not call it phase, because at high temperature there is no phase transition at all. So we call it state. And we are going to have this from this, as interaction increase, we are going to have the metal and then to the motor insulator physics, and we have this crossover physics. And this crossover physics, again, has been studied by many methods, but I would say the signals are still not clear. Our aim is to provide some kind of quantitative, more solid, more systematic check. The challenge here for this numerical study is, since there's no phase transitions, all physical properties are smooth. And our solution now, actually, in this paper, is to study these local spectral functions, which is obtained by these numerical analytical continuations. And we also perform, of course, the systematic check, consistency check with these thermodynamic quantities. For instance, suppose we are now looking at the temperature point 36. Note that it's only slightly above this highest near transition temperature, which happens at 1/3 of the tunneling. For small u, here is for u equal to 5. We can see that this local spectrum has a peak at omega equal to 0. So this is this is a very clear signal for this Fermi liquid physics. So one has the quasi-particle peak at Fermi surface. But if we increase the interactions, then we'll see that now this at omega equal to 0 here, we are going to have a dip. That means at the Fermi surface, that the density of state is suppressed. And we call this state here called bad matter. It is still kind of in the Fermi liquid, but it kind of, I would say, since the quasi-particle weight is not 0, but it's kind of anomalous Fermi liquid. We just take the terminology as bad matter. If we further increase the interactions, we will see this local spectrum weight, this A, at omega equal to 0 is completely suppressed to 0. In these cases, we are going to have a gap at the Fermi Fermi surface. So we are going to have the 3 crossover states. And now we are going to determine the crossover boundaries between these 3 states. One is to determine the crossover boundary between the bad metal and the metal states. And the way we are going to do is to say, oh, when the interaction increase, when the peaks at this at omega equal to 0 start to disappear. At this low temperature, like the T equal to 0.36, we are simply define these spectrum ratios as this. A maximum is the maximum value of this spectrum function and minus this A, the amplitude at omega equal to 0. In the Fermi liquid, since the peak happens at omega equal to 0, Q is equal to 0. And then we do this extrapolation to get this boundary, and also say, oh, we have 10% of this drop to make it uncertainty. So for this case, for this temperature, we get this boundary at about 6.2 with error bar 0.3. At higher temperature, we are going to have 3 peaks, but still our goal is to determine when this peak at omega equal to 0 disappear. So we can do similar thing, but define the spectrum ratio slightly different. And we can also determine this boundary between this metal and bad metal. And to determine the crossover boundary between this bad metal and most insulating state, we use two ways, 2 quantities. One is still, again, use this local spectrum and to see when it will be completely suppressed. We even can simply say, oh, this local spectrum is about 0.1%. But note that we have to be careful because numerical analytical continuation may be not that accurate. And we also use this quasi-particle weight, which is obtained from this self-energy. So we look at this G factor, this quasi-particle weight, as a function of Gill and do these extrapolations. Because we at a finite temperature, we actually do not expect to really have the G factor to be 0. So this is the phase boundary we obtain. It's kind of interesting to see that actually, for instance, the boundary of the Fermi liquid and bad metal, they are not monotonic in the sense when we increase the temperature, this boundary first becomes to the larger U and then bending back. And it does not end at this maximum point for the Fermi for the near transition either. Actually, in this high temperature phase, there are a lot of interesting features. Now I'm going to try to introduce one by one. First, we compute the entropy density as a function of interaction and also as an interaction function of temperature. We do 2 ways. One is calculate the entropy density from this integration as a function of temperature for fixed interaction. So fixed U, and then change the temperature and use this formula to calculate entropy density. We can also calculate the entropy density by fixed temperature and then increase interactions, starting from the free electrons, U equal to 0. So this is a typical curve we obtain. So this is, again, fixed T equal to 0.36. We can see when we increase interaction, the entropy density increase and then reach a maximum point and then drop to a minimum point and then increase again. I will explain this curve later. And the 3 data points are obtained by method 1. We can see these very, they agree with each other. So by this way, we can map out, we can have this map of the entropy density and entropy as a function of temperature and also as interaction strength. This is kind of important for experiments because in experiments, they are not able actually to determine the temperature. What they know with slightly more precise accuracy is the entropy. Because in experiments, they had started with this free electron and then adiabatically increase the optical lattice. And from this map, these isotropic lines, we can see also some interesting effect. So given some entropy, if we increase the interaction, we will see that the temperature will first decrease, and then will increase again, and for very strong interaction, it will decrease again. We get 2 lines, US1, which corresponding to the minimum point of this curve, which actually for fixed temperature, it corresponds to the maximum of the entropy, and US2 is correspond to the max and minimum of entropy for fixed temperature. We get these 2 curves. Now let's try to see that, look at together this entropy density and structure factor, this antiferromagnetic structure factor for fixed temperature. If we, for instance, the T equal to 0.36, if we increase the U, we will see that this entropy will start to increase in this Fermi liquidism. And meanwhile, this short range of these antiferromagnetic correlations will start to develop, but very slowly. And interestingly, we see that when the entropy density reaches the maximum point, when it happens, actually it just coincides with the boundary between this Fermi liquid and bed metal. If we further increase the interactions, the entropy density will start to decrease. And meanwhile, these antiferromagnetic correlations will quickly develop. And the reason for this is that at the bed metal state, the density of state at Fermi surface is suppressed. That actually the charge degrees of freedom, the contribution from charge degrees of freedom to the entropy now is minimized, or let's say does not change a lot. It's small. And here the decrease of the entropy is because the super exchange will help to establish the short-range antiferromagnetic correlations. So the spin degrees of freedom will start to become coherent, and the entropy density will decrease. And when this structure factor, antiferromagnetic AFM structure factor reach the maximum, actually the entropy density becomes minimum. If we further increase, because of this super exchange strength is inversely proportional to U, is 1 over U, and when we fix the temperature, then these antiferromagnetic correlations is gradually destroyed, and then this entropy will start to increase again. So we can really see this physics. From the thermal entropy, from this entropy, if we look at together with the double occupancy, we can also see very interesting physics. The the change of the entropy density with respect to U for fixed temperature can be related to the change of double occupancy with respect to temperature. We know that at very high temperature, then a site can be empty or occupied by a single atom of spin up or spin down, or can be double occupancy. Now, double occupancy density is one quarter. When we decrease the temperature, then double occupancy will start to decrease. That's a kind of normal effect. But at some temperature regime, we will see that if we decrease the temperature, the double occupancy will increase. Let's look at U equal to 6, which is pretty small, correspond to this red line. We will see that actually if we passing from the bed metal to Fermi liquid state, the double occupancy will start to decrease. As temperature decrease, it will start to increase. This is kind of Fermi liquid physics in this regime for small u. Then if we enter these anti-ferromagnetic phase transitions, the double occupancy will quickly drop and then saturate at some point. For large U, we will see that as the temperature enters into the more insulating phase, the double occupancy will start to increase again already. And when we enter the antiferromagnetic phase, it will quickly increase and then saturate at some point. For U equal to A, the change is minor. It's minor, but we will still see this Pomerantz-Cook effect. Now we will try to see that the double occupancy as a function of interaction for fixed temperature. That my previous knowledge actually before this simulation, I was always thought, when we enter this more insulating phase, the double occupancy will quickly suppressed. So in a sense, the inflection point, that's the most rapid change of the double occupancy, will be kind of information between for the boundary between this Fermi liquid and more insulating. So we calculate the double occupancy and also directly measure its derivative as a function of U. And we will see that actually the maximum point of this double occupancy, the inflection point, always happens at around U equal to 6. So this peak location fully sit in the Fermi liquid regime. This is kind of surprising feature we found. And we also look at this charge compressibility. And if at very high temperature, actually a pretty high temperature, we will see that this compressibility, inverse of the compressibility, is kind of linear proportional to the temperature. And this behavior can be easily understood in high temperature because we can simply calculate from this single atom limit in a sense that we just use the single atom statistics. We will simply see that 1 over chi is proportional to T. And if we then use the Nernst and Einstein relation, we will say, although we didn't really measure the conductivity, we will see that conductivity is proportional to temperatures. So the linear T dependence of conductivity originally normally is considered to be kind of signal of the strange metal, but at least for this 3D Fermi-Haber model, that we will see this kind of behavior, but whose mechanism is very simple. It's simply from the single atom limit. So it is not related to this any strange metal at all. But this is a half feeding. I mean, strange metal normally happens at dope cases. So eventually we get this numerical result. That is this phase diagram. We have the phase boundary between this Fermi liquid and we call it bed metal phase. and we also have phase boundary between the insulator phase and bed metal, and we obtain this inflection point of the double occupancy here, that when interaction increase, that double occupancy decrease, and the most rapidly decreasing point is really in Fermi liquid regime, which I have to say we do not really understand why. And we also obtain the, for instance, these strongest when this antiferromagnetic structure factor reach the maximum, which is pretty, how to say, agree with pretty well in quite a large temperature regime with the minimum point of this entropy density. Now that, how much time do I have?
5 minutes.
How much?
Including questions.
I already finished. Okay, then I will stop.
Okay. Questions.
I have a question regarding the turnover of the Fermi liquid regime at very high temperatures. In your case, that would be somewhere between U of 6 and 8, and temperatures, at the very top of the bond, like 0.7. Is that actually physics, or is that because your definition of what means Fermi liquid breaks down?
Can you say again? I cannot really hear.
Oh, okay. So I'll try to speak. Well, I'll try to sit next to the camera, right? So top of your plot, where the green goes into the blue, there's sort of a back turn toward, there's a back turn towards lower U. Is that actually physics, or is that the breakdown of your definition of what it means to be a Fermi liquid?
Very good questions, because this phase boundary is determined by this local spectrum to see that is whether the dip at omega equal to 0 happens or not. So the temperature here is pretty high, as you said. I do not really know whether it's really because of breakdown of the definition of Fermi liquid because the temperature. I cannot answer this question. It's kind of 10% of Fermi surface, right? Fermi temperature.
Let me then ask you, these bars, horizontal bars, is the result of the finite size effect?
Which one?
The bars, horizontal bars. It's like
horizontal bar. This bar.
This and this. It's a result of the finite size, not saturation or.
It's not because this is crossover, and there's not really a very quantitative definition of this crossover boundary, I would say.
So this is for largest size, or how it evolves with this size?
I think it does not really change much about system sizes. Here, actually, for this high temperature here, actually system size 12 times 12 times 12 is sufficient. It's really about there's no sharp information here. We cannot really determine very accurately. I do not really know whether one can have this how to say that has this precise definition of crossover.
One quick, I'll go over here. So one quick last question for the phase boundary, that the red line that you have between the Néel and the isotropic phase. So back in, I would say, maybe 2010 or so, there was an arms race between, diagrammatic Monte Carlo, DCA, auxiliary field Monte Carlo, to get that curve nailed down, and there were lots of results that were basically consistent with inner bars. So are these results still correct, and are yours much more precise or sort of comparable or inconsistent?
Very good question. For small U, actually previous determination of the Tn, I think, is not that accurate, and it was even argued that the near temperature should be below 0.17. And here it said, our information said no, it's definitely not lower than 0.17. Let me try to
Is that also the case with the DCA results? They should be less susceptible to the finite size effects that you're seeing here.
I think DC. Okay, so recently, I think that, for instance, that from I do not really know the DCA result for U equal to 6, U equal to 4, etc. I have to say didn't really know. But recent result by diagrammatic Monte Carlo, they also obtained this 0.18. And for this maximum point, I think that our results are kind of first inconsistent, but the error bar a little bit smaller, and really suggests that the maximum point is around 8.
It would be
You
good to
see that-
see how this compares.
Pardon?
I'm saying it would be good to see how the new results compare to the old results, because I know that, you know, back sort of 2010-ish or 2012-ish, there was a lot of energy sort of invested in getting this, you know, to be precise at a time before experiments were really able to access this regime.
I would say the numerical result about 8 and 9, the number are more or less consistent.
Okay.
Okay, time to continue. Thank you, Jim.
Thank you. Yeah, I will stop sharing.
Next talk is dry cells.
Yes, right. That's probably easier if I do this here first.
Okay, half an hour including questions.
Yes. Don't think that's. Oh, that would be good. So yeah, thanks for coming. My talk was advertised as talking about Pauli path integrals to do dynamics, but then I read that the conference was about precision many-body physics, and there's very much nothing precise about this. So then I got a bit scared. So in the end, my talk will be slightly different, but I did want to advertise this thing. So Nicola, one of my graduate students who just moved, as you can see, to be a postdoc at the Niels Bohr Institute, spend a lot of effort sort of coding up a Julia package that can do many body quantum dynamics. Very hard to hear. Yeah, I don't know what we can do about that. I'm speaking very loud. Maybe there's like a button we can push.
Move up to something.
Oh, it's picking up that mic. This doesn't have a mic.
No, you don't.
Yeah, I think we're talking to this one. So,
Now, this microphone is speaking.
yeah.
Next level.
Can you raise maximum volume?
I could take the internal one. We could try that one. This is already.
Better?
Oh no, this is the speaker.
Massimo, is this better?
I can speak. Is it better?
Much better. Okay.
Oh, much better. That's good. I'll try to stand here so I project my voice. And so basically, I think these ideas are a little bit old, but I think now with the sort of advent of doing quantum dynamics on quantum computers, I think we're learning that they're much more powerful than maybe previously people thought. And so I would say check it out, but I have a one slide. sort of description of a GIF that Nicola is very proud of that sort of describes what it does. So you can find the paper over here. So the idea is basically we do dynamics in the Heisenberg picture, and this is all for spin problems. And so you want to represent your operators in terms of Pauli strings. And so this has some advantage. So if you have your Hamiltonian and you encode it into these Pauli strings, then every time you apply the Hamiltonian to one of these Pauli strings, if you have a local Hamiltonian, actually these strings will just grow, right? They become longer and longer and longer. And I mean, in the end, of course, there's a lot of these very long strings, and that's the many-body problem, that you have to keep track of all the amplitudes of these super long strings. But actually they grow in a very particular way, because every time you commute with the Hamiltonian, every place where there is an identity, nothing happens. And every place where there is some operator X, Y, or Z, you attach it to the Hamiltonian, so it becomes a bit of a longer operator. But if you think, well, so that's, I guess, what's depicted over here. But now comes the trick that actually, if you add a tiny little bit of dissipation to the problem, actually very long strings, they decay much faster than very short strings. Because if I have a string with, let's say, k non-identities, and I add a little bit of dissipation to the system, actually the decay rate of that string, let's say this rate is gamma, the decay rate of that string is not gamma, but gamma times k, because the process is multiplicative, right? So because of this multiplicative nature of how the noise acts on these strings, it basically means that a string of a certain length L decays L times faster than a string of length 1. And you can literally prove that because of that, in the end, this whole path integral in the Heisenberg picture can be truncated. So that's what this package essentially does. So I will have no idea. What is it? I mean, so every time you have a 1, there is an identity. Every time you have an X, there is a Pauli X. Every time you have a Y, there is a Pauli Y. Every time you have a Z, there's a Pauli Z. So this is just the basis for all operators. It's called the Pauli basis. Right? You give me any set of qubits. You have a Hilbert space. Any operator can be written as a linear combination of Pauli strings. The group that this generates is the Pauli group. You see, if you have a tensor product space, every time you can put either 1, X, Y, or Z. If you take a tensor product of all of those combinations, you have any possible operator. But it turns out this is a super efficient basis to do dynamics in, because with a little bit of noise, there is a super efficient way to truncate this path integral. And I mean, you can read it here. But that's basically it. So I'm not going to talk half an hour about it because this was about precise statements. So let me sort of move to the thing I want to talk about, which actually is very much related to the previous talk. So I want to talk about some old school stuff, basically spin models with a lot of disorder, and want to tell you a story about thermal induced order. And so part of this work was done by Aleš, who's actually a team student. And part of it was done by Flaviano and myself. So what are we thinking about the problem? Okay, motivation for the problem is that we want to maybe look at a model like this, which is the random field Ising model. So imagine you have a model of so this is all classical physics, right? So imagine you have a model of interacting Ising spins. They interact all ferromagnetically, so the J's are all bigger than 0, and there's some random field. So this is random field Ising model. This model has some very interesting non-equilibrium dynamics. So actually this has been studied in the past a lot. Basically, there are avalanches in this system. So if you initialize the system in some polarized state, and you basically ask, every time I can find a lower energy state, I will flip a spin. Depending on the strength of the disorder, you can get sort of avalanches where basically spins keep flipping. And the domains that get generated, basically, they span like orders of magnitude in scale. Maybe some of you might know the reason I'm interested in it because I want to understand these quantum avalanches in many body localized systems, but well, they also happen classically. So this seems like a good way to start. But then it turns out this random field Ising model already is like pretty controversial. So basically, there is a whole bunch of papers, and this is just a very small subset of papers that actually make claims that the random field Ising model has a glass transition. So basically, at some temperature, the system will go from a paramagnet into a spin glass. And there is claims of replica symmetry breaking, here the same. There's some RG papers that also claim the same sort of story. So basically, okay, you have a magnet with a lot of disorder, but the disorder is not in the coupling, but the disorder is in the fields. And there's been sort of a lot of papers claiming this is a glass, but actually this is not a glass at all. So in 2010, it was shown by these people over here that actually this cannot be a glass. So what was shown using this Fortin, Castellange, and Nibri inequality, which was actually proven in the 70s, that the following statement is true. If you have an Ising model with only ferromagnetic coupling, so all the J's are non-negative, then actually you can prove that the connected correlator of any two spins for any Jij is positive or non-negative. So basically, there is no way in a ferromagnetically coupled Ising model to get negative correlations between spins. And well, because there is no way to get negative correlations between spins, then if you compute the spin glass susceptibility, well, which is defined like this, well, if this quantity here is non-negative, well, then the Si and the Sj, they're either plus or minus 1, then it immediately implies that the spin glass susceptibility is smaller than this. And that's the ferromagnetic susceptibility. So basically, if there is a transition at all, you just become a ferromagnet, right? Because the ferromagnetic susceptibility is strictly greater than the spin glass susceptibility. But it's maybe even worse. I know that I can always make the ferromagnetic susceptibility finite if I add a small field that breaks the Z2 symmetry, right? Because then I select one of the pure states of this ferromagnet, so I don't get a diverging susceptibility at all. So then this is finite, so clearly then this is finite too, so there's never a spin glass. So it turns out that all of these papers making all kinds of approximations which seem all reasonable actually and predict spin glasses actually cannot be correct because there cannot be a spin glass. But well, now what am I gonna talk to you about? Well, the thing that goes in this theorem, this fact that the connected correlators are non-negative, actually breaks if you have continuous variable models. So the second you move from Ising models to a model like an ON model, where you have vectors that can rotate, this statement is not true. And the simple way to see it, so if you imagine you have an ON model where these S's are now n component vectors, the J's are still positive, but the H's are random n component vectors now. Well, imagine that you just had a ferromagnet. Well, then we all know that basically there are spin waves on top of this ferromagnet. But of course, if I jiggle a spin over here a little bit, well, half of a wavelength away, it will jiggle in the other direction. So actually that means in a ferromagnet, you can totally have negative correlations between spins, right? Just because there are Goldstone modes in this ferromagnet, essentially. So the question is, since we can have Goldstone modes in this ferromagnet, the second we have continuous variable models, can we now get a spin glass, right? And this question is more or less unsolved. So how do we do this? Well, the simplest thing one actually does is, well, first do it on a fully connected graph. Just couple all the spins to all the spins, because then we can do a replica calculation. So basically, we take SI dot SJ, every spin talks to every spin. They all talk with exactly the same strength. So this is just a ferromagnetic model, but there's just random fields over here. Instead of the usual SK sort of model has random J, here there's just random fields. You replicate the partition function and we just compute the exact replica symmetric saddle point free energy, which for the XY model, so for the two component case is given by this pretty formula where I0 is the modified Bessel function. So you can now look at it. So basically the free energy looks like this. So at zero temperature, for example, as a function of the strength of the disorder, if the disorder is very strong, you get, well, one minimum. If the disorder becomes weaker, you see, you get some symmetry breaking, and there's like two possible minima. So this all looks fine. Then if you look at the magnetization as a function of temperature, you basically see that there's a transition from a paramagnet to a ferromagnet, which is magnetized. And if you increase the disorder, the only thing that happens is that this ferromagnetic region becomes smaller. So clearly no glass, because there's just a ferromagnet small. There's something cute, which is actually that if you draw, so this was for Gaussian random fields, but you can actually make a different model where you draw the random field, which is still uniform, but with fixed amplitude. So basically you draw random angles, but the amplitude is always fixed. And then if the disorder is weak, you see exactly the same thing, that there's a transition from a paramagnet to a ferromagnet, which is continuous, but actually if the disorder is strong enough, it becomes first order. So as you can see here, basically, you see at some point over here, you get a first order transition because there's three minima over here, and one of them will become the lowest one. So it looks like in the fully connected case, at least we seem to see a ferromagnet too. But well, you should be slightly skeptical because I have not really shown you that this actually is stable to replica symmetry breaking, because I've only shown you the replica symmetric free energy. And so we put some effort into calculating the stability of this replica symmetric solution. So basically you can take the free energy, you can then take the Hessian of this free energy, so which means with respect to all the different replicas, which we label here with the B and C, and then the alpha and gamma label the components, because we have in this case two component vectors, but we can do it generically. So then, okay, you do some algebra, you work out this Hessian, and then it turns out after some long calculation that if you take the limit of the number of replicas going to zero, which is what you're supposed to do, right? You analytically continue this thing for zero replicas, that there are two distinct eigenvalues. We can exactly calculate them. And so we find that these two distinct eigenvalues look like this. And you see, just like this Ginevra inequality from before, that actually one can use to show that in the Ising case, the ferromagnet is always stable. Well, we get a similar statement over here. So you see that now the connected correlator of the XX and YY determine these two eigenvalues. But there's a small difference, as you can see, well, between this and this in terms of how the averages are being taken. So I guess a plot makes a bit more sense to look at it. So these are these two eigenvalues. So these are the eigenvalues of the Hessian of this model. If you want to perturb it, then check if it's stable to replica symmetry break. And so you see, we find eigenvalue lambda 1 is always larger than 1, except for at one point, and that's exactly the critical point. So there's like a mode that softens at the critical point. And then lambda 2, basically it's gapped. So you have a finite gap in the paramagnet, but then you see it becomes exactly 0 in the ferromagnet. And this is just a statement that there's a Goldstone mode in this ferromagnet. I mean, this ferromagnet is marginally stable, and there's an exact 0 mode that can sort of rotate this magnetization, even in the disordered case, right? So this is basically, your system is super strongly disordered. There is no symmetry in this model, right? Because for each realization of this disorder, the symmetry is entirely broken, but still there is a 0 Goldstone mode in this model, right? So this is a marginally stable phase. There is no replica symmetry breaking. Okay, so now the next part is, okay, I've given you the mean field solution that is for some all-to-all connected magnet with random fields. Now you might want to know, what if I put this on a lattice, right? Maybe there's some more interesting stuff that happens on a lattice. So here's the following thing. Let's add some degree of locality to this problem, right? The simplest next thing one could do is basically to put the model on a beta lattice, right? Because on a beta lattice, I could still compute in principle the partition function exactly. So how do we do this? Well, these are a lot of formulas, but I guess in half an hour I can't really explain everything. But basically on a beta lattice, you can just use belief propagation to exactly calculate the partition function or message passing. Now, so how does that work? For the XY model, for example, well, this is your energy cosine of the difference in the angles and some random field over here. Then if one defines these transfer matrices, which are the interaction between consecutive bonds on this beta lattice and this local matrix over here, which encodes the disorder, it turns out that you can define this kind of messages or cavity distributions that if you solve this horrible looking nonlinear equation, basically you have succeeded in computing the partition function. Okay, so that's what we do. How do we do it? I think Miles might talk about it in the afternoon. One trick to do it is basically, because now in contrast to the Ising case, these messages are not numbers. You know, in the Ising case, since you only have a binary degree of freedom, everything is a Bernoulli distribution. So you just need to pass what is the probability to be up or the probability to be down. So these messages are numbers. But now these messages are functions. So means that you need to compute this integral a lot of times, like millions and millions of times. So you want to do this efficiently. And so how do you do this? One way to do it efficiently is to encode these functions as tensors. So this is like some, and then, well, all these functions are tensors, but basically at the end of the day, you want to decompose them as tensor trains, because it turns out that, imagine you have this function where I have a discretized grid X, where X I store in binary. Then if I put these bits BI over here, by evaluating this kind of tensor, contracting these legs, I can compute this function value. But what's neat about it is basically that, and I'm skipping a lot of steps, that this horrible looking equation over here, which is this integral equation for the cavity messages on your beta lattice, actually can be turned into some tensor network that can efficiently be contracted. And the reason is, again, that just like in all sort of normal tensor network stuff, that in principle, when you compute this integral in a normal fashion, you would be contracting this tensor network from left to right or right to left. But instead, if it's written as a tensor train, you can contract it from top to bottom. And so like this, you can basically get an efficient method to compute these cavity messages in the case where they're continuous variables. And I'm sure Miles will sort of explain it in the afternoon, maybe a bit better. But sort of long story short, like this, if you put in some effort to do the numerics, you can get a reasonable sort of phase diagram, and we can predict the TC. And again, it looks still like a ferromagnet, where there's a transition from a paramagnet to a ferromagnet. But there's sort of a short, okay, here are the cavity distributions. Basically in the high temperature phase, this is a function of the angle. The cavity distribution sort of looks like this. Basically the crosses are showing the exact data from the tensor network, and the lines actually are showing what happens if you fit this cavity distribution with this simple functional form. And sort of this seems to work very well, right? That we can capture this whole distribution simply by having these two parameters, phi and h over here. And this is really the lifesaver, sort of, because it turns out that we cannot scale this tensor network method to the strong disorder case because of huge precision problems. Because the point is basically that you're parameterizing this integral in some linear fashion. But in the end, all of these integrals are sort of Boltzmann distributions, so they span exponentially large scales, right? And so it turns out that you cannot have the precision on your computer to actually calculate this properly. So why is that important? Well, it means that given that we verified that in the weak disorder case, actually this is the functional form, we can now make sort of a next level of approximation and sort of say, oh, what if we assume, so this becomes now a variational calculation, what if we assume that the cavity distribution is exactly of that form? Because then I can solve this integral equation basically analytically. Okay, let me skip this, it's not so important. So that's what we basically did. So once you assume this particular type of functional form, it turns out, and that again, it's quite a long story short, that in the end, each cavity distribution, just like in the easing case where it is a number, can now be parameterized by a vector. So I have an ON vector model, and now my cavity distribution is parameterized by another ON vector. And I just need to pass these sort of vectors around. And there's update rules for these vectors. And again, just like in the normal cavity, there's now a self-consistent equation that you need to solve for these vectors. And if you solve it, you basically find the phase diagram of your model. And so depending on the number of components in your ON model, this self-consistent equation for this update rule basically gets modified. And as you can see again for the XY model, again, it's like a ratio of two Bessel, like modified Bessel functions, just like I've shown you before in the sort of mean field case. Okay, so now what's the story? Well, if we solve at zero disorder, we can pretty much solve this analytically. And again, we see now for the easing case, you see a phase transition from a paramagnet to a ferromagnet, and this looks exactly like you would normally expect, right? But now for the XY model, we already see something funny, or actually for all the ON models, that if you look at this cavity distribution or this cavity field as a function of the temperature, there's like a regime at low temperature where the cavity field actually increases. So it's not a monotonically decaying function, right? And that's kind of, well, we understand why it happens, but I can talk to you about that later. But this is generic for any continuous variable model and has to do with this kind of soft Goldstone modes that exist in the system. And so why is that important? Well, actually, and this is now the crux of the whole thing. This is important because actually it causes some physical effect. And the physical effect it causes is the following thing. So if we now look at the full phase diagram as a function of temperature and disorder strength, then what happens is that, well, at weak disorder, I've just shown you the exact sort of results. You go from a paramagnet to a ferromagnet, but there's some at strong disorder, you're always disordered. There's no transition at all. But there's some intermediate disorder over here where basically there's a reentrant phase. So that basically means that I can give you the system, like the system at this disorder over here, I can give it to you at essentially zero temperature. And if you put it on the table and wait for a little bit, at zero temperature, it would have no order whatsoever. But then if you let it heat up, actually it spontaneously orders. So there's like thermal or entropic induced kind of order. And this entropic induced order is entirely on the mathematical level, basically caused by the sort of increase in this cavity fields. We have a longer story about how exactly to explain that. But yeah, that's basically the story. So again, we looked for a glass in these models because there's a lot of people that think these systems should behave glassy. They actually don't behave glassy, but instead there is at least thermodynamically, they don't behave like a glass. But instead, there's another funny effect that doesn't happen in the discrete case, but is purely an effect of having continuous sort of degrees of freedom, that these soft modes can cause a reentrant sort of phase transition. Again, okay, I said there is no glass, but we can really show this because, again, we can do this kind of Hessian analysis where basically we look at the stability of these cavity distributions that we can show. These are the Lyapunov exponents now of this basically discrete map that you make by solving the cavity messages, and you see the Lyapunov exponents are always smaller than 1. And again, this ferromagnet is marginally stable. It has an exact eigenvalue 1 mode, which is the Goldstone mode of this ferromagnet. Is this relevant for experiments? So we looked a lot, and I think there are a bunch of old school experiments that roughly show this phenomenon. So the oldest we could find is this Rochelle salt, which basically has a transition from paraelectric to ferroelectric. But if you actually cool it down more, it becomes paraelectric again. And so actually this salt was used by the Curie brothers. They discovered ferroelectricity in this salt. So yeah, I think that's it.
Did you try doing the Gaussian propagation not on the major lattice, but on the actual lattice you're interested in?
Yeah, so when I say beta lattice, we do it on a random regular graph. So we do make sure, like wrap it up so that there's no leaves. We have not done BP on a square lattice, let's say. I think we are currently doing actually another type of calculation on a 2D lattice. But yeah, I think we could try it, but we haven't done it now. Just the random field ON model on a random graph. Exactly, random regular graph.
Including the lattice?
No, that's not a random regular graph. So on a Cayley tree. Right.
So what's the definition of random?
Random regular graph, the definition is that basically each node has exactly the same amount of neighbors. That's what the regular refers to. So everybody has the same amount of neighbors, but they're randomly connected. And you can prove that basically in the thermodynamic limit, the thermodynamics is identical to the one on a beta lattice. That's why it's useful.
But beta lattice has no loops, and this thing can have loops.
Exactly, but you can prove that the density of loops goes to 0 in a random regular graph. So that's the whole point. So it's like a controlled way to get a graph which doesn't have, because the problem on a beta lattice is that you have as many leaves as the bulk of the tree, right? So you don't want everything to be determined by the leaves. So you can have this is a random regular graph. So basically it doesn't have any sort of, because everybody has an equal amount of neighbors in contrast to the leaves over there. But actually you can calculate the probability to have loops and they're irrelevant.
It's a mathematical result because.
Yes, exactly.
Okay, next question.
Yes.
Oh yeah.
Started saying that at the beginning it was in everyone knows that
Right.
picking up.
Right.
Which are the key ingredients you need to have this phenomenon? Can you find it in this model you studied?
Well, that we haven't solved. I mean, that's what I want to solve. But then basically, because there are all these people that sort of were claiming that these avalanches are basically due to metastability and glassy physics. But actually, if you look at the thermodynamics, there is no signature of a glass at all. This is totally not glassy. I still do not quite understand what then is the defining feature that gives these avalanches. But we're trying, we can maybe talk about it more concretely later, but we're trying something else now, basically a similar thing to what people would do in spin glasses. It's to look at the dynamical phase transition. So maybe this has a non-trivial TD, but we don't know.
Okay. Zoom over directly.
So I can connect it directly to I use Zoom on my laptop or. Can the remote people hear me? Do I need to turn on my microphone or will it?
I don't know. Nobody is there.
There are a few people.
Oh no, Massimo is there.
Yeah.
Massimo, can you hear?
I might need to turn on my microphone.
Actually, this should pick up.
That can the remote viewers hear me? Can we get a signal or? Okay, it's just assume they can. If they can't, just let me know and I'll turn on my microphone on my laptop.
Okay. I don't see any signal for that.
Okay. Do you see the? I don't know. I don't see. Started. Can we just move this slightly?
Sorry, we can see meeting note. Can you swap the displays?
Oh,
I think you should start talking, it will automatically focus on you.
Yeah, this should
yeah, okay.
start talking.
All right, yeah, let me know, the remote people, if you're having trouble. All right, yeah, thank you for having me here. So currently I'm at the Amazon Center for Quantum Computing, located at the Caltech campus. Sorry. Go. And so I'm going to talk about this work, which is in collaboration with Nicola and Ashley, also from AWS, as well as Johnny Gray and Garnet from Caltech. Okay, so we're going to be talking about loop expansions, focusing on tensor networks. I'm going to begin with a very quick overview. Before I do that, I'm going to have, in keeping with official Amazon policy, I'm going to have a non-skippable advertisement. Okay, so this is something, Qubit Factory is something I just developed for fun, but it's a puzzle game where you solve tasks in quantum computing, mainly aimed at beginners, but there are also some challenging things in there as well. So please check it out or share it with people who may be interested. All right, so today's talk is going to be a very tensor network-based talk. Unfortunately, I don't have the time to go through tensor networks in any detail, but tensor network, you have a network of these multi-dimensional array of numbers, and our goal is to contract this to a scalar, okay? So this could just be some giant summation over these multi-index arrays. Okay, why do we want to be able to do these contractions? Well, there are a lot of powerful many-body simulation algorithms based on tensor networks, okay? So this could represent a partition function, it could represent a quantum state, it could represent a path integral. Many things can be sort of formulated as contracting a tensor network. All right, so and what I'm going to show you today is that this problem of contracting a tensor network can be formulated as solving a belief propagation and then adding some additional loop excitations back into this approximation. Okay, so, and this is really similar type of series expansion to what you may do in, say, quantum field theory with a Feynman expansion, where you expand out the propagator in these different orders of processes happening. Okay, and so from a practical perspective, what we're doing is taking something, a large tensor network, which could be very difficult or expensive to contract, and we're approximating it as a sum of much simpler things to contract. Okay, so this is some, hopefully some way of making tensor network approximation simulations are much more computationally efficient, especially for, say, 2 or 3D lattices. And this is very surprising for someone who's, I've worked in tensor networks for many years. It's very surprising that this sort of thing works. Like naively, these are very complicated objects, very complicated sums over all of these tensors. You wouldn't think that you would just be able to decompose as a sum over all of these terms, but yet somehow this, I'll show you that this does indeed work. All right, so before we begin with the main talk, I'm going to give a very brief introduction to this idea of belief propagation or message passing. Okay, so this goes back many decades in computer science as well as statistical physics. Okay, but for us, so we're going to use this idea to try and contract a simple tensor network to a scalar. Okay, and the idea is that on each edge of the network, we introduce a pair of messages. Okay, so these are just some vectors in this notation. Okay, so we could just introduce, say, a random pair of vectors on each index, and then we have some scheme for updating these messages. Okay, so the outgoing message on a tensor is given by contracting all of the other incoming messages. Okay, so if I want the outgoing message on this index, of B, I contract in the incoming messages on the other indices. Okay, so I could do that, say, for all indices of B, and I get a set of 3 outgoing messages on the indices of B, and then I could move to a different tensor and do the same thing. So I do the same thing for tensor E here, and I have another set of 3 outgoing messages by contracting the incoming messages. Okay, so very simple, very cheap. Even if I had a very complicated graph or network, this would still be very cheap and easy to implement. Okay, and so that's the idea. I should keep doing this for all tensors, and hopefully I'm going to converge to some fixed point messages where all of these equations I showed you are simultaneously satisfied for all tensors. Okay, so that we call a BP fixed point. Once we have that, then we can hopefully approximate this complicated sum here as a product now of scalars. Okay, so if I contract each tensor with its incoming messages, I just get a scalar out. Okay, so we've gone from something which is computationally very difficult to something which is computationally trivial if we've reached this fixed point. Okay, and so if I have a loop-free network like a beta lattice or any other tree network, then BP is guaranteed to be exact and to always converge. If I have anything with loops, however, then there are no guarantees. This may work, this may not work. Even if this works, then it may not be very accurate. So even if I get a fixed point, it may not be accurate to the physics I want. Okay, and my own interpretation of this, like I've seen this before, and I really wasn't convinced that this would be good. It really doesn't look like it should be good at all. But then I saw this very nice paper from Joseph Tyndall and also Miles Studemeyer from Flatiron, and they have this very nice result that sort of convinced me that there was something really nice here. Okay, so the paper from Joseph, what they were doing was simulating this experiment run by the IBM quantum computing group. Okay, so IBM, they have this 127 qubit processor. They ran an experiment on this processor. This experiment was designed to be difficult for classical methods to simulate. Okay, so I won't go into the details here, but it's just by the nature of the experiment, it's too difficult for many sort of standard either exact methods or matrix product states, which is a DMRG-based simulation. That was also too expensive. Okay, and if I plot the actual experiment as a tensor network, we could formulate this experiment as trying to contract this tensor network here. Okay, so this is sort of a dense 3D structure of tensors, and you can see like this looks like it would be very difficult to try to evaluate this sum in any sort of even approximate way. However, as I said, this paper from the Flatiron Institute, they use BP as a key ingredient to solve this problem. So it was actually relatively easy to implement this belief propagation method here. And it actually worked very well. Okay, so they got very good results, very in line with the experiments. And it can actually be done very cheaply, like a few minutes of computation time, if it even gets pretty good results. All right, so belief propagation, message passing has some really strong selling points. It's very easy to implement numerically, and it's very computationally cheap. Okay, however, there are also some very strong drawbacks. So belief propagation, if I try and implement it, like for one, it just may fail to converge completely. Like I just don't ever get a fixed point. It just oscillates forever. Even if the belief propagation does converge to a fixed point, it still could be completely wrong. Like it could just be not at all related to what I'm interested in. However, there are lots of cases where BP does converge and the result is reasonably good. Okay, and I'm actually going to focus on these cases today. So there are a lot of work within this belief propagation community of sort of fixing these first 2 points. There's a lot of sort of generalized belief propagation methods that are better at converging for fixed points. But today I'm going to assume scenario 3. Okay, so that I'm going to assume we have the case that the belief propagation works and is reasonably accurate. Okay, and my goal is to have some systematic way of improving this. So let's say belief propagation gets us within 10% of where we want to be. Can we get to 10 to the minus 2% or 10 to the minus 5%, or like going from qualitatively accurate to quantitatively accurate? All right. So let's begin the actual main part of the talk. Okay, so as I said, we're going to assume that we've found a BP fixed point. So I have, let's say, a simple tensor network of 4 tensors, and then I can approximate this by this product of scalars that's just given by putting in the fixed point messages there. And the goal, what I'm going to do is try to reintroduce some of the things that BP lost from the network. Okay, so I'm going to call this the BP vacuum, and I'm going to reintroduce some sort of excitations on top of this BP vacuum. Okay, let me show you my notation. Okay, so each edge of the graph I'm going to resolve in terms of a BP fixed point plus some projector onto the orthogonal space. Okay. Okay, so then sort of just trivially, we can expand this simple diagram. Each index can be resolved into the BP part plus the orthogonal part, which I draw in red. Okay, so we just have this, these 16 or however many diagrams, just trivially expanding all of these possible combinations of fixed point versus projector. Okay, so that's not particularly convenient to work with. We'd have exponentially many diagrams. However, we have this very nice theorem, which tells us that any configuration that has a dangling excitation, so if I have any tensor that has a single index in the non-BP vacuum, then this configuration will have 0 weight. Okay, and let me just go through quickly why that is. So if I have a dangling excitation, then I just expanding this out a little bit. Okay, so I have a single index in the now in the excited state. If I apply my BP equation to this dangling end, then I just push through the fixed point message, and now I have a contradiction where I have a message multiplied by the projector onto the orthogonal space. Okay, so this just just if I have a BP fixed point, then any configuration that looks like this automatically has 0 weight. Okay, so that's very nice. It tells us we had all of these expansion terms that almost everything is 0 except for the thing that contains the closed loop. Okay, and so this is sort of the basis for our expansion. We only need to consider things that have closed loops and things that don't have dangling edges. These are the only things that could possibly add back on top of the standard belief propagation. Okay, so let's try a slightly more challenging network. So I now expand out all of the loopy configurations. Okay, so again, this is an exact expansion. I haven't lost anything here. But even then, if I've considered all of the loop contributions, there'll still be very many as I go through a larger graph. So I still need some way of sort of simplifying these down. So one observation we can make is that if I have sort of 2 different separate loop configurations on top of this vacuum, these are completely independent. So these, if I think about these as excitations, these are non-interacting excitations. Okay, so this simplifies things a lot. We only need to consider the simply connected configurations. And if we go for, and the second observation is that if I'm going to call the degree of the excitation the number of excited indices it contains. So we can also argue that the low degree excited configurations should be the most important ones. Okay. And I'm just going to use a similar argument that we used to say correlations decay in tensor network states. Okay, so if I look at configurations of larger and larger degree. So each of them I can sort of resolve as a transfer matrix to some power that gets higher and higher. Okay, so as long as the spectrum of this transfer matrix is strictly less than 1, then these terms are going to get smaller and smaller. Okay, and it's a very simple argument. If the spectrum of the transfer matrix was equal to 1, then I would have many other problems, and that I would have some huge degeneracy in my space. Okay, so this has to be the case that I have some exponentially decaying weights, or belief propagation just wouldn't work to begin with. So, all right, we're doing pretty well. Yeah, so very simple approach here. We just find the BP fixed point, and then we can just add back these loop contributions. So starting with the small degree terms, adding the high degree terms as necessary. Right, so how does this work in practice? Okay, so I'm just going to show you a simple benchmark case. So we're starting with this AKLT model. I'm going to do it on the hexagonal lattice because it's slightly easier, but we can do it on other lattices too. Okay, so this is just, we just have some Heisenberg coupling. It's squared and cubed of that term. And this model is very nice, and that we can represent the exact ground state as a simple tensor network. Okay, so this is called a PEPS, a projected entangled pair state. And it's just, we have a very nice analytic solution in terms of this tensor network. Okay, so it makes it very convenient to work with. At the same time, this is sort of a non-trivial example in that this ground state is SU2 invariant and translation invariant. So it's not close to a product state. It's not something completely trivial here. Okay, so we're going to use this to study, use this method I've described to study this tensor network state. The first thing we're going to look at is evaluating the norm of this state. Okay, so we take our tensor network state. This is like the ket. We contract it with the bra state, so we have sort of doubled up our indices, but now we have a closed tensor network representing the scalar norms. And we're not actually, so the norm is not actually very interesting because it goes to infinity or it goes to 0. What we're actually interested in is sort of the free energy density. So the logarithm of this normalized by the number of sides, which is generally a finite quantity. Okay, so here's the result. So, okay, so I compute this free energy. If I just use belief propagation, so I would get 0.2% error. So this actually works surprisingly well. Like I have this 2D quantum state, this ground state of this AKLT model. Just this very simple approach of belief propagation already gets me a reasonably confident result. However, by adding in these loop expansion terms, so adding in the degree 6, degree 10, degree 11, degree 12 terms, we can reduce this by many orders of magnitude. Okay, so we really, as I said, we go from something which is sort of qualitatively accurate to something which is sort of quantitatively accurate to very good precision. And so this was for this particular case of the AKLT model. We can do a similar thing where rather than the AKLT model, we just initialize a completely random tensor network. So this is just some essentially random quantum state described via PEPS. And again, we have a similar result where BP does pretty well to begin with, but we can improve on BP by several orders of magnitude by having these loop terms. Yes, question?
No, 5 minutes.
5 minutes, okay.
Graciously.
Okay, so that was just for a scalar quantity, the free energy density. A lot of the algorithms, what we actually need is some kind of matrix or tensor quantity. Okay, so for instance, if I cut open a single index from this network, if I do the contraction, now this would evaluate to a matrix, so some kind of transfer matrix. And this is actually if we're doing some kind of iterative optimization scheme, then the transfer matrix is what we need to actually update this tensor network. Like if we're trying to find a ground state of some Hamiltonian you give me. Okay, so again, we can apply this belief propagation approach. So the belief propagation itself will give us a very simple term here, and then we can add back all of these loop contributions to this matrix. So all of these individual terms also evaluate our matrix, and we just sum them together with some weights that I'm not going to explain. Okay, and again we get very similar results where the transfer matrix itself, like leaf propagation, already gives us something pretty good, like 1% error, but we go down to many orders of magnitude improvement by adding these loop contributions. Okay, these dotted lines represent what you would get if you did the calculation by exactly diagonalizing a 6x6 or 8x8 or 12x12 lattice. Okay, so really we get more accurate than if you exactly diagonalize the 12x12 lattice, which is sort of the best you can do roughly. Okay, yeah, and this works. As I said, the hexagonal lattice was the easiest, but we also did it for the Kagome and the square lattice, and we get similar results. Although the square lattice is sort of worse and also slower to converge, and you can just sort of realize this: the square lattice has many more loop corrections, and they sort of proliferate much quicker as well. So or the loops are much shorter, so you expect this to be worse. Okay, but it still works in practice. Okay, so let me just say, in future, what we really want to do is, okay, so usually if we're trying to evolve with this PEPS tensor network, so one way we can do it is sort of try to quasi-exactly contract this 2D network. So you start from the boundaries and you contract in with some transfer matrix approach. So this is called the fill updates method. It's very accurate, but it's very expensive. That the dimension of the tensors you can deal with is roughly 12 or so. You could also do a simple update for PEPS, which is rather than trying to contract in this whole environment, you just use the local environment. So this is very cheap. I can do much larger dimensions, but it converges much worse. So I would say one of the main selling points of what I've described is that now we have sort of a systematic way to sort of go between these two approaches. Okay, so we can improve on the simple update systematically. We can still potentially go to very large dimensions because this is very cheap. So we could do still with crazy large dimensions of greater than 100. But as I said, we can improve on the simple update by many orders of magnitude. All right, yeah, so let me just summarize. So I've sort of described the general strategy for just resolving a tensor network. I don't need to know where this comes from or what it represents, but I could potentially resolve this as some kind of vacuum plus these loop excitations that live on top of this vacuum. Okay, and a lot of my research career has been sort of trying to find better ways to sort of brute force these networks. So thinking about contraction ordering, thinking about approximations and local moves. But what I would say is that this work sort of just is a different tool in our toolbox where we can use some kind of series expansion as a general approach for contracting tensor networks. And just a comment, like often series expansions are sort of the first thing people discover or apply in terms of many-body physics. Here, it's really taken a long time to figure out a way to do this for tensor networks. And I would say that this is really because there's no obvious small parameter. If you just give me a tensor network, there's no small parameter. Like I would not have thought something like this is possible. However, if this belief propagation works, what it's implying is that there is this small parameter that we can expand around, and the small parameter is somehow related to the strength of these loop correlations within this network. All right, thank you for your attention. I think that's everything.
There's some sort of versions guarantees that you can give, that, you know, some limit in which you're guaranteed to go to the exact result? And are there,
The only guarantee you have is if the loops, if you don't have loops or the density of loops goes to 0, like we saw. So you can like you could first converge for a beta lattice or something like that, or some kind of tree approximation to the actual lattice you're interested in. As soon as you have loops, you don't have any guarantees.
It's behave to work with 1D or quasi 1D systems, like ladder operation, not exactly 1D.
1D, I mean, any 1D system I would typically represent as a matrix product state, like use DMRG. BP is exact for that. So it's really only 2D that you start to need belief propagation anyway, because 1D is exactly contractible without belief propagation. But belief propagation also is just a slightly different way of doing the same thing exactly for 1D.
Got it.
There's not an obvious how well this works is not obviously related to the entanglement in some way. Yeah, it's not something we understand very well. There could be, you can have examples of very strongly entangled states with very long range correlations where this still works very well. It depends on how you're representing your state as well as the properties of the state itself. Yeah, it's trial and error. There's no good understanding or theoretical guarantees.
Okay, then let's think.
I'm gonna use this mic.
I think it will.
Okay. Natalia, how do you start the slideshow?
Think you need. It's a full screen. Yes.
Now maybe this.
Okay, myself here.
It's too full.
Let me remove myself. Okay.
I think maybe
Dated. Oh, probably this one.
perfect. Yes. All right. Can people on Zoom hear me? Stick. All right. Okay, thank you very much, first of all, to the organizers for inviting me. This is one of my all-time favorite workshop. So it's great to be here and hear about all the different methods and systems people are studying. Today, I will talk about the dynamics of the spin boson model and how it can be studied efficiently with real-time quantum Monte Carlo. And specifically, I'm going to focus on the short and intermediate time dynamics and how we can extract the transient dynamical phase transition from that data. This is work done with my collaborators, Kai Cohen, Peter Chen, and Moshe Goldstein, and please check out our paper on the archive about that. So the spin boson model, it's a fixed impurity model that consists of a spin or two-state system that is coupled to an infinite bath of harmonic oscillators, so non-interacting harmonic modes. And originally it was introduced in the context of dissipation in quantum systems, and the Hamiltonian formalism energy is conserved. So in order to have dissipation, you can couple it to a really large bath. And of course, harmonic oscillator is sort of the simplest thing you can do. But it's also relevant in the context of interactions with photons, and you can even study Fermi systems via a mapping called bosonization. So the Hamiltonian of the model has the following ingredients. First of all, we have the spin, the two-state system. We have epsilon, the energetic bias, and actually in this talk, I'm going to consider only unbiased systems for epsilon equals 0. And then delta is the tunneling between the two states, the diabatic constant. The sigmas are Pauli matrices, so this is just a simple 2x2 matrix. Then we have the harmonic bath, which is just...
Excuse me, can
Yes.
you please share your screen?
Oh, it's not shared? Okay. Sorry about that. Thanks, thanks for bringing that up.
Thank you.
Okay, great. Thank you. Yeah, so just very quick. Oh, there should be a button to maybe so if you click on more, and there should be hide floating meeting. Okay, perfect. Great. So yeah, we haven't gotten very far. So we have the spin boson model and the spin, the bath Hamiltonian, and then we have the coupling between the spin and the bath, which we assume to be linear. The CK characterize the strength of the interaction to the kth harmonic mode with frequency omega k. And in the bath hydrodynamic limit, we can characterize this interaction by a spectral density that can be expressed in the simple smooth form. At low frequencies, it behaves like omega to the power of s, and then at large frequencies, there's some kind of cutoff. People consider different types of cutoff. In this work, we consider an exponential cutoff, but it can also be a sudden cutoff or Lorentzian cutoff. In this omega c, this cutoff frequency defines essentially the relaxation scale of the harmonic bath. Now, depending on the value of this parameter s, we have very different physical regimes. If s equals 1, that's called the ohmic case. That's perhaps the most studied, most maybe also physically relevant case, but so a lot is known in this case already analytically. If s is greater than 1, that's called super ohmic case. And in this case, the tunneling always outweighs the recoupling, so the system is always delocalized. That means equally likely to be found in either of the two states. So that case is really simple to solve. Now, the sub-ohmic case is what I will focus on in this talk when s is between 0 and 1, and it has a really rich physical diagram. It has a quantum phase transition, zero temperature, and a lot of other interesting phenomena that we will discuss. I also want to highlight the role of the initial condition. So here we consider the factorized initial condition where we prepare the spin, we just hold it fixed in one of the two states, and the bath is assumed to be equilibrated just on its own without the spin. But other conditions are also possible. So for instance, you could equilibrate the bath together with the spin while holding the spin fixed, and then let the system go and so on. And actually the initial condition does matter quite a bit. So what we're interested in is the dynamics of the system. And for that, we need to perform our diagrammatic expansions in real time, which of course is very challenging. So we need to perform a Keldysh contour expansion. And kind of in a nutshell, if we consider just schematically the time evolution of any kind of observable, and so if we write it in real time, so if there's no time dependence, if we're working in equilibrium, then we can just cancel these two time-dependent terms because the operators all commute past each other. And so then we do what we always do. We can just expand what's left over, rho naught, in imaginary time. So expanding something like e to the minus beta h in imaginary time and do a typical expansion. But if there's a time dependence, then we cannot do that. Or if in this case, we have a quench. So we don't start out our system in the equilibrium state, but in some with some different rho naught. And so then we need to find the new equilibrium. So for that, we need to consider the full Keldysh contour. For instance, we could start at some time t max. We could propagate back along the blue line to time 0, then back along the red line to t max, and so on. So that requires a more involved expansion, and also that we do work in real time. And so schematically, we put our observable on the Keldysh fold at t max, and then we do our vertex insertions, kind of like we do in equilibrium, but this time on both branches of the Keldysh contour. We can then unwrap this contour and perform our updates in a similar way to how we do it in equilibrium. Now, how can we make efficient real-time updates? That's a big challenge. So in this work, we use the so-called inchworm algorithm that was developed by my collaborator, Guy Cohen. And so the idea behind this efficient algorithm is that we expand the ball to the full propagator just by a short amount in time each time. And by doing this, we can sort of recycle our knowledge from previous time steps in the next subsequent time step. And by doing these expansions, by just short kind of inchworm steps in time, we significantly improve the scaling so that it reduces from exponential to polynomial, and that we can achieve good results in reasonable time. Now, specifically for the spin boson model, we employ two types of expansions. And since this is a precision workshop, I'm going to briefly review how we do the expansions before I show you our physical results. So the first expansion, kind of maybe the first one you will think of, is the system bath coupling expansion. So we're expanding in the interaction part of the Hamiltonian H int. And if we do that, then essentially our H int and the interaction picture splits into a system, time-dependent system part, and a time-dependent bath part. And so then we can look at the expansion separately. For the system part, it's really simple. Our propagators do have matrix form, but it's just a simple product of sigma z's times 2 by 2 Green's function. So we just insert our vertices, and then we have a product of matrices. And for the bath part, essentially we have our typical Wick's theorem. Everything is a scalar. So we just write down our Wick's theorem and consider all possible combinatorial ways of connecting these lines. You can also expand differently. For instance, you can expand in the tunneling. So in delta times sigma x. And if we do that, then you utilize the fact that so if you remove this part, then all that remains commutes with sigma z. So the spin gives you a well-defined quantum number, and everything factorizes into two distinct subspaces, then can individually be diagonalized with a canonical Poisson transformation. So then you have a system part for your sigma z observable that's essentially just flipping the spin over and over by the action of sigma x. And because you need to start and end in the same spin state, you can only have an even number of these spin flips, and there's also a phase potentially that depends on epsilon. The bath part is more involved. So actually here you have a ratio of multiple time propagators. So you have kind of this more complicated object, but all vertices are connected with each other. So every vertex is connected with everything else, and it's not shown here, but they're also connected with the initial condition. So you kind of have this blob where everything is connected, and that's a problem if you want to do any kind of bold expansion, because you cannot cut these vertices easily. So you have to be a bit more tricky about it. And so specifically what we do is first we do a moment expansion. So first we explicitly sum all possible combinations of putting our time indices on either branch of the Keldysh contour. We sum them into moments, only even moments contribute. And then on top of that, we also do a cumulant expansion over these moments. And so if you do that, the advantage is that since you've already summed over the two branches of the Keldysh contour, you don't have quadratic scaling in time, but just linear scaling in time. And then you can go ahead and you can do your usual Baire and then bold expansion, and you can apply your instrument step. So these are the two expansions that we use. The sort of hybridization-like expansion in the spin-bath coupling works really well at low temperatures and works well at weak coupling. The cumulant expansion of the diabatic expansion works very well at high temperature and at strong coupling. So there are some regimes where they both work well. In some regimes, only one of them can converge reliably. So this is a good consistency check that you get great results. So I'm not going to show you too many benchmarks, just one here where we compare with the numerically exact multi-layer, multi-configuration, time-dependent Hartree approach. So the black lines at 0 temperature for these parameters here, we cannot work explicitly at 0 temperature, but we can work at really, really low temperature where there's no more temperature dependence. So that's effectively like 0 temperature. And we see a really excellent agreement for both expansions within the short and intermediate time dynamics with these 0 temperature results. And so we did a lot of other benchmarks as well that make us confident that this method works. So what do we want to actually look at? So I promised you that we would look at non-equilibrium dynamics. Specifically, we'll look at the population difference. So expectation value of sigma z, the difference between the occupation of the two states of our two-level system. And we start out quenching into one state. If you didn't have any interaction, it would just oscillate forever. Since we have an interaction, it's going to be damped. And you can see in this picture that we have 4 regimes of interest. So first of all, you can have coherent oscillations, but as you increase the coupling, so I should say alpha is the coupling here. So that's what characterizes how strongly the system and the bath interact with each other. As you increase the coupling, these oscillations vanish. So you have coherent and incoherent regimes. You can also see that at long times, you can either become delocalized, so equally likely to be in either spin state, or you can retain some memory of your original state. So that's the localized base. And so we want to consider transitions or crossovers between coherence, incoherence, localization, and delocalization. So here's a bit of a more detailed characterization of the dynamics. On the top panel, we have S equals 0.2, so that's really deep in the sub-ohmic regime. Bottom panel, S equals 0.8, so closer to the ohmic regime. On the left, we have low temperature, and here we have high temperature. And I'll mostly talk about low temperature, but towards the end, I'll show you also some high temperature results. So you can see, of course, as you increase coupling, the system becomes more localized as expected. And you can also see that it becomes more incoherent as expected. But you see that especially this change from coherence to incoherence happens really differently depending on your value of S. So if in both cases, of course, amplitude gets damped as you increase the coupling. But when you're closer to the ohmic regime, there's also a change in the frequency itself. These dashed lines are an analytic approximate prediction. So there seems to be a kind of interesting interplay between two mechanisms of the incoherence transition or crossover that we're going to look at in more detail. And then at high temperature, well, it becomes less localized, less coherent. And also you can see I kept sort of the lines from this figure. You can see that the frequency also shifts a bit. And I will show you that in more detail as well. So quick note on how we analyze the data. We do heuristic fits that very well describe the short and intermediate time dynamics. So we have a damped exponential component, so a damped oscillating component, pure damping, and then potentially an offset. And the presence of this offset characterizes whether we're localized or not. And these very simple fits actually describe the data really well. So I'm going to show you the frequencies and the damping rates and offsets extracted from these fits. Now, let's talk about the localization transition. It is known in equilibrium, so at infinite time, that there's a quantum phase transition between the localized and delocalized phase. And it's known that it's associated with a critical exponent that's 1/2 if S is smaller or equal to 0.5. So of course, we cannot really look at equilibrium because it takes very, very long time to reach it, orders of magnitude longer than what we can access with our method. So what we look at instead is this, what we call transient dynamical behavior. So what can we extract from our intermediate time? If we just look at this and we extract the offset from this, what will it look like? And it actually looks really differently from the QPT. So we do see signatures of a transition. There seems to be a kink at specific critical values of the coupling, but the critical exponent is not 1/2. It's something that's greater than 1. So it's a totally different behavior at intermediate times from what it is known to happen at very long times. Another really interesting aspect is the decoherence. Well, usually in the literature, it's described as a crossover. So there's a crossover from coherence to incoherence, but we actually identified 2 mechanisms of that crossover, of which one is damping driven. So if we look at the frequency divided by the damping rate, then yes, indeed, we have kind of a smooth falling off, and we can arbitrarily set a threshold where omega equals to gamma, and that's going to be the damping driven crossover. But there's another change from coherence to incoherence that's frequency driven. And that one is actually a sharp drop to 0 frequency that's more reminiscent of a transition, but that happens only at large values of S at low temperature. So only for S greater than 0.5, at least within the alphas that we were able to study with this method. So there are totally different mechanisms at play here that both cause this change from coherence, from coherent to incoherent behavior. This is a summary of our dynamical results, kind of phase diagram between localization and delocalization, as well as coherence and decoherence. So the red shaded region is our confidence interval on alpha star. That's where we observe going from localized to delocalized phases. And for comparison, I also plotted from a different work, alpha C, that's the critical alpha for the quantum phase transition in equilibrium. So at low S, they seem to agree, but they do seem to deviate quite a bit at large values of S. And then the blue and the green lines are the 2 different characteristics of the coherence-decoherence transition. So the blue line is the frequency-driven transition, which we only observe up to certain values of S. And then the green line is the damping-driven transition that is distinct from the frequency-driven one. I also wanted, okay, so a couple of minutes, I just wanted to briefly mention the role of the initial condition. So when you're in equilibrium, doesn't matter how you got there, but since we study dynamics, the initial condition matters a lot. And here's just an example of the factorized condition, which is what we use, versus the equilibrated condition, where the bath and the spin are in equilibrium, with the spin being held fixed. And you can see that the short time dynamics So what you should compare sort of these two lines with the green line. So this line here, this is from this work. So you see that the dynamics is totally different, right? This even at 80 omega CT is pretty localized still, while ours is already delocalized. So it's going to take a really, really long time for this to become delocalized. And that's another sort of hallmark for why the dynamics has such different properties from when you work directly in equilibrium. And then finally, these are newest results that are not published yet. So we're looking at finite temperature. And I wanted to highlight that as you go from low temperature to high temperature, well, the system does become more delocalized. So kind of all of these lines shift to lower alphas. These lines shift to lower alphas. But here, when it comes to the frequency-driven transition, we also observe that the sharp drop, so it happens earlier, but it's now also observable at lower values of S, which is kind of interesting. You also see this interesting original increase in frequency before the drop. And then finally, if we make sort of analogous phase diagram plots as a function of temperature, so starting at low temperature and then going to higher and higher temperature. So we don't see really very much in alpha star. There's also quite a thick error band. But we see, for instance, that if we look at the interplay between the incoherence transition and the localization transition, that kind of the blue and the green line move down a bit in comparison with the red shaded region of the localization transition. So there seem to be also some interesting physics there. So that brings me to the end of my talk. There's a lot more that we can look at, even considering fermions through bosonization. And yes, I hope I could convince you that that's a very interesting system with rich physics, that its dynamics is worth studying, and that we can get really great and accurate results with Inchworm real-time quantum Monte Carlo. Thank you.
Questions?
I was rushing because I didn't want to be in the way of lunch.
Okay, so this is for single speed.
Yes.
Is it feasible to extend this method to more than one spin with the same breath?
So more than one spin has been studied. Actually, this this work, they also consider two spins. It's going to be much more difficult with the Inchworm Monte Carlo. It's possible, but I don't know exactly. Like, I haven't tried, so I don't know if it's realistic with the computational resources we have. Typically, the more impurities you add, the harder it gets. So
let's say you do Monte Carlo in imaginary time, and then let's say continue real-time continuation. If you compare.
Well, okay, so if you compare the scaling, but from adding an extra impurity with for real time, but well, I mean, real-time Monte Carlo has worse scaling. Typically, we have quadratic scaling in time, and not so much the cumulant expansion, but it has other limitations. So then that is going to be that is going to get worse as you add another impurity. So it's going to be linear versus quadratic. But I cannot say for sure because I haven't tried.
So you mentioned these polaron transformations sort of work in one regime kind of well. So now suddenly I was wondering, is it known or clear if you do like a dynamical transformation? So you would do some TDVP, like time-dependent variational principle for this polaron transformation, how well it captures the dynamic?
Oh, I don't know. So we variational. I mean, we don't.
So you can do like some kind of Lilov binds or like Firsov transformation, but dynamically, right? So in a time-dependent way, is this kind of known? Whether this captures the physics or not?
I don't know. I'm sorry.
Right?
Oh, I can ask.
No.
Is it possible to study two bars talking through a screen?
Yeah, that's, I skipped it, but that is one of the things that we're looking at. So, specifically what we want to look at currents through the spin. Yes, that's possible. And there's some codes that have this capability.
You can get real time.
Yeah, yeah. So that's also something that it's been put a bit on the back burner, but I think we already have a code that has the capacity to do that. No, you can absolutely do that for, so it's essentially the same structure of the code as for the Anderson model. And yeah, another thing that we're interested in is combining actually the bosonic and fermion bath in one. Yeah, so sort of in terms of how the algorithm and the codes are built, it's very transferable. So it's the same ideas. The only thing that changes is the nature of the propagators, but the data structure is essentially the same. So it's very nice and easy to go between the two. And yeah, with full counting statistics, you can do these kinds of systems. So yeah, that's definitely on the to-do list. Next projects. Mhm.
Okay. Room. Yeah. So yes.
Yeah. Oh,
Now I know.
Thanks for it.
Now I know.
Just.
Okay.
So let's see, Zoom, it's just the same Zoom that we're using to view, I guess. Okay.
So we just share the screen.
Okay. Okay. And then my pointer is just on my computer, so that.
You can do the full screen.
Let's see. I thought I did.
I think I need to do it.
No, it's
It might be on that side.
outside screen.
Mhm.
Oля.
Hmm?
Oля, it's from his computer.
Are you sure? I mean, I see this.
I don't, yeah, no, I think it's
Oh,
not.
maybe this one.
So.
Oh, yeah.
I think it's one of these. So maybe immersive? No.
Okay. It's full screen. It should be.
Here. Okay.
Oops. Switch.
Oh, we're seeing.
I didn't start and play. That looks
Oh.
good.
Okay.
Perfect. And which microphone is being used? So people on Zoom, can you hear?
I have my microphone muted.
So if there's a problem over the Zoom, please unmute and speak because we will not see the chat.
And I can turn my mic on if that helps.
Yeah, just
Well,
turn it on
Right,
just in case.
okay, that's a good idea.
Well, we don't want feedback.
Yeah, well,
Yeah, but I think maybe just the mic will not cause feedback. I have my playback turned off though. Let's see.
Right, okay,
Okay,
shall we start?
try that.
Great.
Great.
Test,
Test.
test. Oh,
Yeah, that is
causing like a speaker to play.
kind of weird.
Yeah.
I'll turn that on. Okay, great, I'll get started.
Okay, let's welcome to the second session, and I'll start with our first speaker.
Okay, thanks, Olga, and thanks for the organizers for inviting me. It's nice to be here, see a lot of familiar people. So I'll be giving you all a nice, just a brief talk, about just some work we've been doing over the last year and are continuing to push. So this is just kind of telling you about the beginning stages of it, and I'd be happy to get your thoughts and feedback about understanding it better and where we could take it next. And it's this idea of trying to do time evolution, but in the complex plane to get time-dependent correlation functions. So the motivation is, as many of you may know who work with Monte Carlo or you work with tensor networks or other methods, is that straight ahead real-time evolution often is very difficult, scales very poorly, even for tensor networks, right? So often people think of tensor networks, if you use them in this mode, you say, some methods can't do time evolution, but tensor networks can. They can, but it's still very expensive. So it's not as bad as it could be, but it's still very frustrating how expensive it can be. And this basically is because of growth of entanglement. I don't know if I have a slide on that, but tensor networks are limited by how much entanglement there is in the state. And fundamentally, when you're time evolving a state in real time, the entanglement generically will grow in many problems, especially say a quench problem. So this on its own is not such a good idea. So the point of this talk is to show how we can go around this problem by just evolving in the complex plane. And the idea is that we can gain in terms of lower bond dimensions and therefore reach longer times. And then the nice part about all this is that we can also controllably reconstruct the real-time properties that we want from the information we get on these complex contours. So we're never going to see the state evolved in real time, but we'll see some properties of the state evolved near real time. And then we can do this multiple times or in different ways and extrapolate back in nice ways. And I think the set of ways will continue to grow. So this is actually based on 2 papers. So 2 groups thought of this idea right around the same time, and we were in touch with each other. So you'll see like Olivier Parkelet appears on both papers. And it's just for reference, I'll leave these papers up. They're now both published in PhysRev-B. I should have updated that. So I'll break down the talk along the lines of the 2 methods in the 2 papers, because I think it shows the range of ideas here and how much more could be added to it. So quickly, motivation is that tensor networks are a very appealing method because for equilibrium problems like getting ground states or finite temperature, they're by now for say low dimensional problems, very efficient and accurate. And you can see that that's continuing to be the case to more and more problems, like Glenn's talk showing earlier that new methods are coming along in 2D as well. But this is just showing some of the kind of pinnacle of like the best of low dimensional tensor networks, in my opinion, like this recent paper from this year by Ian McCulloch, showing that with newer tweaks to DMRG, you can just get these incredibly good convergence, like you can get convergence digit by digit by digit by digit in very short times for sort of 1D problems. This is a slightly older paper, but very nice, showing how you can get very good estimates of like power law behaviors out to, orders of magnitude in distance and these kind of coupled wires and things. So it's a very precise method. But I'd say the status of doing real-time evolution with tensor networks is not as satisfactory. And as I said a minute ago, the problem is that the resources in tensor networks are these bond dimensions, these internal indices connecting the tensors together. And these just generically grow in many real-time evolution protocols if you want to work at a fixed accuracy. And that's bad. So it basically leads to like exponential growth of cost. Why do we need to go to longer times? Like what would be the reason to do this? Apart from just fundamental interest in quantum dynamics, at CCQ down the street, we're quite interested in pushing these embedding frameworks like DMFT. And in DMFT, where you take some kind of 2D or 3D problem, and you have a means to map it to a 1D kind of problem, some impurity problem, the main thing you need to complete this loop and close these equations is some kind of time-dependent correlation function, like the Green's function of the impurity site coupled to all these effective bath sites. So that's an example of like a problem where we need to reach longer times and have more accuracy and lower costs, because you're going to do this a bunch of times. We don't need to go to crazy times. We don't need to go to times of 1,000,000. We just need to go maybe 4 times longer than we currently can, because these properties will decay. So we just need to go a little longer and more accurate. And how do things look right now, and how much better could they be? If you do kind of standard, basic kind of real-time evolution with MPS and do some windowing of the tail and some standard Fourier transform analysis, and you look at the self-energy, which is this, property about the interacting information in the Green's function that's really important for this DMFT loop, you see that as you look at the self-energy, so again, it's just some property of the Green's function, right? As you go down, order of magnitude lower and lower in frequency, things are okay at high frequencies, but at low frequencies, i.e. at long time information, the standard approach just completely is wrong. NRG is really the thing to beat. So we're showing here NRG results are the, I think the, one of the two curves. I think it's like the, just the solid curves. Oh, no, sorry, that's the thick bands. And then this new method I'll be telling you about is able actually now to match NRG down in these very low frequency limit. So that's exciting to us. So we'll come back to that result. What motivated this also is that this is just kind of to advertise some other things that I'm really interested in, just to show you all how much is going on in the world of like classical algorithms for quantum systems, is that there's, I'd say, a ton of activity right now of different groups and different approaches thinking about how we could access quantum dynamics in new and really intellectually interesting ways. So one example of this is to revisit perturbation theory, right? Which sounds like this old, kind of dead as a doornail idea, but actually is getting kind of a new life in this way, which is to say that you can think about going to very high orders, and you have these functions. In this paper, they call them Q, and they're functions of like time differences. So you can think of Q as taking a bunch of time differences. So imagine Q as just being some expansion of the Green's function just on this quantum dot, sorry, this impurity site, like a quantum dot. So there's no spatial variables, you just have these times. And this function can be computed pointwise. So what this group did is this involves some people at CCQ and in France. They actually used a kind of radical type of like tensor network machine learning algorithm to evaluate this function at a set of maybe like 1,000 points and interpolate the rest of the function. And you can do this to like order 30. And then you can evolve to basically any time you want to very high accuracy. So they've basically solved a lot of like quantum dot problems of certain kinds this way. But it's quite an involved method with lots of technical moving pieces. And then another motivation is a very different approach some people have been doing. It's called like influence functional. It goes by different names. Is to imagine writing like a Keldysh, double in time path integral, and then you can actually compress from the side this path integral, viewed as like a trotterized tensor network, and find that when you compress from the side, you can use a matrix product state to do that. And so now people are researching in this in more detail and saying there's this idea of temporal entanglement. I'm not really sure if it's entanglement, but somehow these properties are low rank in time. And so people are exploiting this to also go to very long times, like this group of Jonathan Keeling was able to simulate quantum dots coupled to bosonic modes representing phonons to, I think, a time of like 1 million, literally 1 million. So on a regular kind of workstation level calculation. So these are really interesting approaches. So it's motivating us to think maybe the problem of solving real-time dynamics is kind of cracking. Emmanuel's been involved in some of this work too, so I probably should have mentioned your work as well. But I would say one mild criticism of these two approaches is that they're kind of complicated, right? You couldn't just try these at home so easily. There's lots of technical stuff you have to build up to do it. What if you just have like a regular package where you can time evolve in MPS? So what if you can just call PDVP, it's just this kind of black box function. Could you use that and still get some similar results? Yes, question.
Are you solving time-dependent problems or time-dependent dynamics of static? What's the problem?
You could do either one. So this is all at this point kind of generic. It's just say some initial state and you apply like let's say the simplest case would just be static Hamiltonian, and you just want to start in some non-Eigen state and then just time evolve it forward. So it could.
It's a simpler problem than time dependent.
That's right, yes. But I believe I think in both approaches, especially this one, having time-dependent Hamiltonian is also fairly easy to add in. So you would just have the properties would just depend on where you are in the time direction. And so these, for example, these gates, this is just a trotterization of your Hamiltonian, the part of the Hamiltonian acting on the dot. So you could make that really arbitrary. Yeah. But this method, it's not like solving everything. I mean, this method is sort of currently mainly working for 0-dimensional quantum problems. zero-dimensional interactions, I mean, coupled to an arbitrary path that could be three-dimensional or anything, but it's not like this is going to let you just time evolve some kind of uniformly interacting 3D quantum problem. Not even close to that yet. Also, part of the game here is that you're only asking for certain properties. Like you maybe can't get the fidelity out of this, but you can get certain correlators out of this. So that's kind of the game. So our motivation was, can we just do something simpler? What if you just have the ability to time evolve the state? So it's well known by many groups working on this problem that imaginary time evolution generically goes quite well. If you do imaginary time instead, quantum Monte Carlo can do it, tensor networks can do it, things just evolve to the ground state, entanglement doesn't grow. I mean, it doesn't grow arbitrarily, it might just grow to some plateau. So things are nice. But then you have a different problem. Technically doing this, there's enough information to recover the real-time dynamics. This is a well-known fact. There's a formula. It's just that it's very ill-conditioned. So any error you make, it's going to get blown up by this process. So the information is sort of there, but it's just very hard to extract it to enough accuracy to really be useful for a lot of problems. And there have been some really nice approaches where people are fighting against this very hard. So there's work on using machine learning approaches, like neural network approaches, to solve this so-called analytic continuation problem. There's work by, for example, the group of Anders Sandvik about kind of constrained sampling methods and where you can put in some beliefs and priors about maybe where there's discontinuities or peaks in the resulting spectral functions and things, and then fit the rest. And these are working actually quite well. So there's a lot of progress there. But again, these are kind of complicated and technical and require a lot of expertise to manage. But if you think about just the ability of NPS codes, you can technically ask the code to evolve along any contour. It's not like Monte Carlo where things are a little more restricted. You really can just say, give me any arbitrary path in the complex plane, and the code can at least try to follow it. It's very trivial to modify the code to do that. And we also know that if you're on this imaginary axis, things are easy, you have low entanglement, but you have low information about the problem. You're going to have the same issue with the analytic continuation. We know on the real axis, you'll have high information, but your entanglement's high, everything will be slow. So this is kind of begs the question of like, why not try to do some balance? Why not go at 45 degrees or some other path that maybe you kind of balance effort and information? And then the question might be, is this just a smooth, kind of crossover from hard work and high information to easy and low information? Or is it quickly get easier as you go away from the real axis? Maybe if you're just epsilon away from the real axis, do things dramatically suddenly get better? What actually happens, right? So to benchmark these ideas, we were interested in these impurity solving contexts. So we did this single impurity Anderson model, just a interacting kind of Hubbard model type site coupled to a non-interacting bath. We just took this kind of standard, if you did it in real space, it would just be uniform hopping in the bath. Here, this is written in energy space. And then the quantity of interest for us is the spectral function. So that's just where you time evolve and then measure C dagger and C at different times on the impurity site. And then you get the retarded Green's function. And from that, get the spectral function. And also you can get the self energy. So that's just the context. But this is really for us in a way, just like a practice problem, thinking about if we could use these in DMFT to close that DMFT loop. But that's just one question I'll say at the end is that, it's by no means is this method a priori limited to these kind of problems. These are just the ones we picked. And these methods should be tried more on other kinds of problems. And then some initial exploration already shows a bit of promise. So you take some different contours in the complex plane and you run DMRG to get the ground state, act with an operator on the impurity site, like either C or C dagger, start evolving in time, and you just map out the entanglement entropy that you see. And as expected, if you march down the real axis, the entanglement entropy just grows and grows and grows. The costs blow up a lot. Things get very slow. You can usually only reach times, that are in the tens. It's not very nice. But then if you try these other contours, like this tilted contour or this parallel contour where you go up a bit in imaginary time and then across, you see that all of them have much lower entanglement entropy, and it doesn't grow very fast, if at all. So already things look kind of promising there.
Another question?
Sure.
Seems to me that it's sort of a general problem from the kind of complex analysis. Is there even a simpler playground? Just take a spin, one up in a time-define magnetic field, which is not even analytically soluble. So wouldn't it be sufficient to test some of your hypotheses?
Well, the only thing is for us, entanglement is the main resource. So maybe if we did two spins, then we'd be in business. It would be a good idea just to try. What I think what would be good to try is there's a really nice paper by Kieron Burke about what's called the Hubbard dimer. It's just it's like Hubbard model on 2 sites. And you can show that it has like tons of physics, like weak correlation, strong correlation, all these different regimes. You know, we could just try that actually. That would be a nice, we're thinking of just doing some more free fermion studies actually, of just big systems too. Yeah, go ahead.
So is it the case that like just a pointer in that plane, it doesn't really matter how I get there, like it would just be a fixed state here.
Mhm.
So you could understand like this parallel state as the time evolved state with some weak projector or two.
Mhm. That's right. So I don't know if I say this on a slide, but our intuition for say, we're mostly going to focus on this contour later, is that it, like you said, it's just kind of a projector where you just almost like remove the high energy part of the state. You just say, whatever state I started with down here, think of it as the ground state, but I act an operator. So now it's a non-eigenstate. So it sort of technically has weight on all the eigenstates, right? You just remove the high energy part.
Yeah.
And that's what this will
It's
do.
just
Yeah.
taking the equivalent of taking the real time evolved state, just
Mhm.
evolving it towards the ground state for a small amount.
That's exactly right. And again, I don't know if I have a slide on this, but I think the intuition I have right now is that it's kind of maybe kind of obvious is that if you think about what would make the entanglement grow at short times, it's probably just like dephasing of the high energy states because those change the most rapidly by definition, you know. And so all the short time differences from the initial state must come from like high energy part. And so if that's gone, that whole short time part maybe is a lot slower changing now. And so entanglement 2 might be slower changing and so on. So this is also something that calls for like a more careful investigation. I think probably one could prove things about this in certain cases and study exactly solvable systems more, and all this I think should be done. Great, but yeah, your point is an interesting one too, which is that if you do all these calculations exactly, the entanglement is just associated with points in the plane. So we could imagine making like a heat map of it. There may be some interesting effects though about truncation, which is about, you know, if you work at some fixed resources, you take different paths, you'll make different amounts of error. So there's a little bit of a question there. That's probably kind of subtle.
Yeah.
Mhm. Like non-reversibility of the code sort of, but I think that's probably, we can kind of push that away with just converging things. So one point about this is, so let's say we take this contour, right? One pedagogical point here to make is that this will just give you the wrong answer. I mean, I'm not saying that we're going to take this as the correct answer. I mean, you could try to do that to some crude leading order kind of thing, but let's just see what you get. So if you just pretended this was the right contour and not, you know, if you pretended this was real time, what would you get? So you would compute this kind of, you know, complex time Green's function, do the usual part to get the spectral function from it, and this is what you would get. So the solid orange curve here is the correct spectral function for the example problem, and then this dashed curve is what you would get if you didn't attempt to correct it. So you see already it's interesting, some kind of low frequency features are sort of roughly there, but of course it's quite a bit off from the real thing. Not surprising, right? Because it's not the correct contour. So we need to correct it in some way. So then this is what the 2 papers were about, was 2 very different ideas for how to reconstruct the correct results from the ability to do these cheaper complex time calculations, right? So that's the point I hope I convinced you, is that they are quite a bit cheaper because you saw the entanglement being much lower, right? So how do we analytically continue or otherwise reconstruct to get the real time correlators from these complex time results? One thing we can think about is we have the freedom to choose any shape. So we only need, let's see, what was my point here? So the idea is we can stay closer to the real time axis, right? So with the imaginary time approach, you're sort of forced by your method to stay really far away from real time. Here we can stay closer to real time, so the reconstruction might go better. We only need to make small corrections, and we can choose any shape we want. So we can kind of optimize it or adapt it for convenience to make the code easy to write or to make the costs low and all these other things. So this is something we're now working on getting more quantitative about. So far we've mostly just done kind of empiricism on this. So here's the first method. So this was thought of by former postdoc at CCQ, Xiaodong Cao. So the idea was to say, consider some fixed shape, but have like a deformation parameter alpha. And the bigger alpha is, the more you deform this contour away from the real axis. And the shape actually won't matter. The method takes that all into account. So you just pick some kind of rather arbitrary shape. And Xiaodong picks this shape where it sort of curves up and then flattens out and goes in a straight line. But you don't want to take alpha too big because you're hoping to make the problem kind of kind of invertible. So then you define this kind of generalized Green's function on this complex contour. So you have this, now t is some kind of internal parameter that tells you how far are you moving along this contour. And then the main trick is that you can define a Taylor series expansion in alpha. So you could say, let's expand in alpha to some order, then we will plug alpha equals 0 into the Taylor series to try to get back to the value where alpha was 0. And so I'm going to skip over a lot of steps, partly because this is a shorter talk, and also the steps are like very boring. They're just things you could work out in Mathematica or on paper. But there's some coefficients you do in the Taylor series. Most of them are purely just things you can work out with calculus on paper that have to do with the shape of the contour. They don't involve any many-body physics at all. It's just pure math. But there's only one part in the formulas that involves many-body physics, and it's these numbers that Xiaodong called phi n. And what these are ultimately is that you're time evolving your state to some distance along the contour. And then, unlike what you would normally do to get G, where you would put C dagger and then the ground state again, you put H to the power of n in between. So there's some kind of modified time-dependent correlators where you put H to the power of n. So the bottom line is you just need these numbers up to the n of the order of the Taylor series that you're going to do. And then you put them back into some complicated but straight ahead formula that gets you all these coefficients of this Taylor series and lets you shoot back to alpha equals 0. So that's the idea. It's a nice idea because the contour shape is just handled by the calculus for you. And one neat thing is that in practice, you only need, I think I may say this in the next slide, but you only need really low orders, like 3 or 4 for n for this to work. So, so Xiaodong just took these orders of like 3 or 4 and alpha to be somewhere between 0.1 and 0.5. And then here's the kind of results you get. So if you do the usual real-time approach with this windowing and then trying to go as long of a time as you can on the real-time axis, you get results like this. So you push the bond dimension from 20 up to 500, and you see even at 500, you have all these wiggles and artifacts and things. And it's a lot of work and the results are still kind of disappointing. But with this Taylor series and complex time approach, just a bond dimension of 30, which is quite small in the MPS, and this kind of 3rd or 4th order expansion and so on, you get great agreement with these reference results. And you get really nice kind of correct behavior at omega going to 0 that obeys certain known sum rules and things like that. So all these details come out nice, no wiggles, good agreement with the benchmark results. So we were quite happy with that. And I don't think I have it on the slide, but I believe Xiaodong was able to reach a time of like 100 in that calculation because of how much easier it was to go on this complex contour. Okay, and then also when you use this method to get the self-energy, this is how you get these results I showed, where you can go down multiple orders of magnitude in omega and get great agreement with these NRG reference results, which are kind of state of the art for this problem. So that's really promising. Okay, that was all I had to say about that method. So any questions about that Taylor series method? Okay, great. And then I'll briefly tell you about the other method, because I think it's just interesting how, already there's 2 quite different ways to solve this problem. So the other method is just to take a very specific and very simple shape, right? So the previous method, the shape was kind of arbitrary. We didn't explore that many shapes. Xiaodong just had this nice idea of like kind of curving up and plateauing, but the Taylor series took care of those details. Here, it's a somewhat more analytical approach where you pick a very specific shape, which is that you march an imaginary time up to some distance tau, then you make a hard right turn and go in real time on a parallel contour like this. So the nice thing about this approach is that for certain quantities, you can just analytically derive the relationship between this complex time spectral function, this kind of deformed spectral function, and the actual spectral function in real time that you really want. So there's just an actual formula in frequency space. So really, once you get, this is the thing you would get following the usual prescription, but putting in the complex time data. In principle, all you do is you go frequency by frequency and just divide by this number and immediately get the real-time result. There's only one problem with that, which is that when you go through some arguments about accuracy of Taylor series and this kind of inversions and things, the fact that this is a non-analytic function at omega equals 0 causes practical problems and you lose accuracy due to that. So yeah, that's what I said on this slide. So there was a nice method, I'm not going to go into the details very much, by Olivier Parcolet, where you can basically fix this problem by just doing the evolution 3 times. In practice, there's a trick really where you only do it once and you do some backwards imaginary time evolution and do these different sandwichings of different states to effectively have done it 3 times. That's some extra details in the paper. But let's just say you just did it 3 times. You get these 3 sets of results. you make a linear combination of the results and you choose the coefficients of this linear combination carefully to smooth out this function that you're going to divide by at omega going to 0. And you can basically make it analytic up to some higher order. And then this makes the division much nicer and everything goes a lot better with, when you get into details about floating point and Fourier transforms and things. So these nice tricks were worked out, but you see this is all kind of analytic stuff. So you have a lot of clarity in terms of what you're doing, why is it working, all of that. And they get similarly good results. So this is their self-energy results. And you can see, again, excellent agreement with NRG. And one nice thing about it also, besides the kind of analytical understanding, is that it's practically cheaper than this Taylor series approach, because you don't have to do these extra computations, putting in powers of H and doing these extra correlators and stuff, which can be pretty expensive, actually. And then they were able to push their method to actually a pretty complicated calculation. It was this 3-band impurity model that they treat by actually taking a tree tensor network. So they have this rather complicated tree tensor network with impurities located at different points in the tree, and all these different chains coming off representing different Bath approximations and things. So it's a nice method, just showing how far already they can push it. So that's all I was going to say. Basically, just thinking about this method, why does this work? Like, why is this even possible for this to work? I would say that a narrow view of our job as people, implementing classical algorithms of quantum system is to say we must simulate quantum mechanics, right? Our job, the physics is unitary time evolution of a wave function, so we must do what the physics is doing, right? That's kind of a narrow view that some people might take, especially say if you're comparing to like a quantum computer, right? People say, there's that quote by Richard Feynman about, nature is quantum, damn it, so you must, use a quantum computer, this kind of thing. But that only really makes sense if you have this kind of narrow view where our job is to imitate nature. But our job is not to imitate nature, right? Our job is just to get the answer, right? So we can cheat like crazy. That's kind of the point, right? Similar to like complex analysis, right? You think your job is to do the integral, but your job is just to get the number that equals the integral, right? So you can go off in the complex plane and do all kind of tricks, right? So that's kind of what we're doing here, right? We only wanted this correlator. We didn't need the wave function. We can get the wrong wave function, but just extract the property we want out of this sequence of wrong wave functions. That's the game, right? And then this was the slide where I was raising the point about that Glenn raised, which is to say, why does this work in more detail? This is where we need some people to do a little more careful theory. We just didn't have the time yet to dig into this, but basically this initial imaginary time evolution part that was there in both contours suppresses high energy states clearly. And apparently these contribute a lot to the entanglement. And I think it's not hard to understand why, but it would be nice to see somebody work through that more carefully and kind of say how much entanglement depending on how far we go and all these kind of things. And then I think most interesting to me is that as you go in real time, it's not like the high energy states come rushing back. Like they stay away for kind of a long time. And this I don't totally understand, but it's just kind of interesting to see. Because remember those entanglement plots, they stayed really pretty flat for quite a long time. And so, the implications here is that this could really be tried in any method, not just tensor network methods. So neural quantum states could try this, quantum Monte Carlo could try this. Each method may benefit in its own different way from being off in the complex plane and not on the real axis. Also, I think the methods for doing this recovery will get more and more precise and cheaper and nicer. And it'll be interesting to see how well it will work for uniformly interacting systems and for quenches and other kinds of problems. Maybe it won't work for every kind of problem, but already it seems like it'll work for quite a wide range of interesting problems. So this is just the summary of the talk. So thanks, and I'll take any other questions.
Thank you.
So you can only do this to calculate the temporal correlation function in the ground state. If I really want to do a quench problem, you do not avoid the fact, the entropy of the state below.
I think it just still depends on what property you want, right? So because nothing in the method really depended on what initial state I picked in terms of running the code. I mean, the results might depend a lot, but we just have some initial state that's an MPS. We just run a time evolution code on it. We can tell the time evolution code steps to take, and we can say, on this step, go in this direction in the complex plane, then go in that direction, And then we get a bunch of properties, and all we need is some theory or some reason, either this Taylor series or that Fourier transform analysis. And you just have to tell me what property you want. And then I just have to be able to come, think through and say, there's enough information and I can bring it back. But you know, if you want the fidelity or something, that may not be such a nice property, but any other kind of low weight, you know, local property may be fine.
With the local, you mean like
Correlation functions and yeah, low order thing.
I did not ask question about entropy and
Maybe. I mean, it just because there's always one thing you can do that's very simple. That is too simple and we didn't even try it. Is literally just go different distances above the time you want and just make a plot of the property and just like fit it back to zero. I mean, you could even just try that, right? So if the property doesn't, it's not too crazy at the shape as it goes back, you could always just try fitting it to a straight line or something. Yeah.
A quick question again related to the actual path we take. I would have thought, as you say, there could be some numerical differences, but like, have you tried like going as far as you can on the real axis, and like going up a bit on the imaginary axis, and then going like doing as much real time as you can, and only then going off the real axis a bit, and then pushing that as far as you can, then going a bit further.
It's a good idea. We're talking about this right now quite a bit with our sort of math expert, Jason Kay at CCQ. And I've been raising more or less some version of that question to him because he's really interested in the question of, can we make kind of a designer method that delivers like good accuracy at all omega? And I think your method, what you just said, would be kind of a first step in that, because you would get all this high energy stuff really, really well. But then you would say, okay, it's starting to cost me too much. Let me kind of start to lose a little bit of that. But I've already got it because I've already gone some way in time. And now I'll kind of target medium frequency, then I'll target low. You know, so there may be ways to kind of just zoom in and zoom in and zoom in and kind of get all the frequencies in different ways. So we're thinking through that right now. Yeah. Thanks.
Are you going around in a circle?
Oh,
Come back and close. I mean, typical way would be to
Yeah.
go off towards infinity and then. But
oh, that's
you can
interesting.
go in a
You mean
circle.
like in complex analysis where you close the contour and
Well,
Or-
if you close the contour, you can do a Fourier transform, then you
Yeah.
know the function along a line. And then there are tricks, you know, see two tones.
so you mean something like maybe going to the right in real time and then closing like back that way or
Right,
something?
and so then you
Yeah.
can map this onto,
Mhm.
and because we know the analytic properties of these functions, it's actually
Yeah.
very easy to then progress. So
Exactly.
That's something we should talk about.
We should talk about it. Yeah, we've also had some discussions about that. The point being that, you know, these don't have pulse in the, you know, so a lot of contours have to equal each other. So there's a lot one could play with there.
And can you evolve backwards in imaginary time very easily? Or?
Oh, this was something we tried too. So that Grindner paper, the second one, does this a little bit. And we were debating of like, they didn't show the entanglement data. And we were like, does it grow much or not? It seems to grow pretty fast. At first I thought, why would it grow? But then I thought more, and I think I know why, but it seems to be pretty bad.
If it diminishes going forward in imaginary time, must grow going backwards. Yeah.
Seems that way. Well, I was thinking that maybe the anti-ground state is also low entanglement. So maybe an infinite negative imaginary time, it's good again. But I think the problem is it goes up. I think it goes up first, then comes back down. So I think it's bad in the middle or something. Yeah. Okay. Yes.
Should I do? Should I connect it to?
So you have the Zoom?
Yes. I directly
I
just the
think
Zoom.
it's easiest if you.
Then the Zoom is.
So it's through Zoom.
Through Zoom, yes. I do
It's
that.
simple.
Okay.
Is it basically taking
Share screen.
and putting the other one directly. A little bit more of that. The body system is. So it's almost like there could be some. That can work in small.
It's perfect.
There's like computers, they all.
Yes, okay. So, thank you for being here and thank to the organizers for inviting me here. It's, I confess it's my first time in New York, so I will take some days to go around as well. So I'm afraid my topic would be a bit, less on the high precision side. I will try also to present, I will present also some numerical results, but I will try to give you more like an overview on this research topic. So I'm currently a postdoctoral fellow at ETH, but the work I'm going to present you is about a project that I started during my previous position at KTH in the group of Igor Babaev. And it's about, let's say, a new kind of fermion condensates that is formed not just by Cooper pairs, but some objects that involve more than 2 electrons. So let me start by acknowledging all the people involved in this work. So as I said, I've been working in the group of Igor Babaev, and this work, I mean, I've been collaborating also with Johan Karlström, Daniel Weston, Julien Garot, and many experimental groups. I will present some of the experimental results as well. And then I will focus on a more recent work that I've done in particular with Igor and Johan. So as my title already anticipates, we are going to talk about some fermionic condensates that goes beyond the standard pairing paradigm. So as you know, the paradigmatic, let's say, fermionic condensate are Cooper pairs. Within a Gisborne-Landau picture, we can introduce a complex order parameter, and we can describe all the beautiful phenomenology associated with superconductivity in terms of this phenomenological theory. So we have this complex order parameter, which is 0 above the critical temperature, even in the case where Cooper pairs start forming and we have a finite density resulting in a change of this potential shape, the system can remain in a non-superconducting state until it reaches global phase coherence between these Cooper pairs, spontaneously breaking the U1 gauge symmetry associated with this mode. And then, of course, we have all these beautiful phenomena, zero resistance, Meissner effect, magnetic flux quantization. Well, so far so good, but as you can see in this picture, there is not really space for something else, especially in a weak coupling, let's say, limit. We cannot actually stabilize objects that involve more than 2 electrons. So what can we do? How can we have this more exotic phase? So in this introduction, I will try to guide you on how to realize this kind of higher order electron condensate in a very, let's say, simple way. So the first ingredient we need to realize these states is essentially multiple species of Cooper pairs. So we need a multi-component superconductors. This can be the case of multi-band superconductors or even single-band superconductors with some unconventional pairing, or some mixture of charged condensate where more species like electronic or protonic Cooper pairs can form. On the right side, I will just do, let's say, an example to show you what is the underlying mechanism to realize these kind of phases. So I will start with the easiest extension of the Gisborne-Landau standard picture by considering 2 components. So 2 species of Cooper pairs, meaning these 2 complex order parameter. Then the second ingredient I need is some intercomponent interaction between these 2 species, such that in the ground state, the system breaks some additional symmetries. So not just the U1 gauge symmetry associated with the superconductivity, I don't know what is it. Okay, it's fine, but some extra broken symmetry. So again, let's continue with our example. I just written the focus. How can we adjust the focus?
So focus of the image?
Maybe but then it's on
It's on
Zoom.
Zoom, yeah. It looks good on this laptop.
Yeah, I don't know. I'm sorry. Yes. Okay. Try to go. So essentially here I'm just writing twice the free energy functional without any direct coupling between the 2 species, which however talk to each other via the electromagnetic field. So this indirect coupling is already enough to give you some more extra physics. And we can see it more clearly once we rewrite the free energy in this way to highlight which are the physical mode of the system. And these are the standard, let's say, superconducting mode, that is the one coupled to the electromagnetic field, which is a charged mode. And then we have another mode associated with the phase difference, which is neutral, and is a sort of superfluid mode. So already with this, we have this other key ingredient of having two broken symmetries in our ground state. Finally, the third ingredient is something that is able to destroy the coherence among Cooper pairs of the same species without destroying the coherence among pairs of Cooper pairs. So something that does something like that. And in this case, I mean, one way of realizing this is to consider phase excitations, and in particular, topological excitation of the phase. So in the case of a two-component model, we can have more than one species of topological object. We can have vortices in the individual component, either in the component 1 or 2, but we can also have composite objects, so composite vortices, where the phase of the two condensates wind around the same core, either in a co-direct or in a counter-direct way. And these objects are the key object to realize this intermediate higher order condensate phase, because they are such to affect just one of the two sectors. And we will see it in this example. So in this toy model, we have a ground state, which is a superconducting superfluid. So the phases of the two order parameters are ordered in the ground state. And we can define these two order parameters being different from zeros. Now we can imagine that by raising the temperature, the first topological excitations proliferating are this kind of composite vortices, co-direct. And this is actually a good hypothesis, since these are the cheapest object in energy to proliferate. And if this is the case, you can immediately see that they will destroy the superconducting order. They will restore the U1 symmetry associated with the charge mode, but they are completely harmful for this other mode. So they essentially do not affect the phase difference, because the phase of the two condensate wind in a coherent way. So essentially, their proliferation drive the system into an intermediate phase, where the system is no longer superconducting, and also where the two order parameters have mean value that is 0 in this case, but there is a residual order, and this residual order is in the phase difference now, and this can be expressed in terms of, let's say, an order parameter that is quadratic in these bosonic fields, and then it is quartic in the fermionic fields. So this is an example of what is called fermion quadrupling condensate. Of course, by raising the temperature, these composite vortices will split apart and we restore the normal metal phase. This is not a new idea, of course. There have been people, and many of them will be attending this conference. First of all, Anatoly Kuklov, who actually worked a lot on these ideas, both on the idea of fermionic higher order condensate and bosonic higher order condensate. And tomorrow we will also hear one of the last development by Egor and Boris on these fields. So today we will focus on this fermionic higher order condensate, and we will see which has been the new development in the last years. So to summarize what I just told you before, essentially we have seen that these phases can emerge as so-called vestigial or paired phase from a ground state with multiple broken symmetries by the proliferation of these topological excitations. So in general, this phase can appear both above the superconducting critical temperature, and this is in general associated with a residual order in the phase difference of the condensate, or they can also appear below the superconducting critical temperature. And this is the case of the charge for each superconducting state. I don't know if you have heard about, where essentially the residual order is in the phase sum. So, okay, we already mentioned that these ideas are around since 20 years, but what about the experimental detection of these phases? Well, actually, 3 years ago, the first experimental observation of such fermion quadruplet condensate was reported in an iron-based superconductor. I will just very briefly show you the result. So this was the previous phase diagram. This is a phase diagram as a function of the doping. So this material is doped with the holes through the insertion of this potassium. And as you can see, within the superconducting phase, in a certain range of doping, it appears a state that also breaks time reversal symmetry. And this is essentially due to the fact that across this Lifshitz transition, you are in a situation where the interaction between these three bands is equally repulsive. So there is a phase frustration between these three phases that can be described via this Gisborne-Landau re-energy, where all these Josephson coupling are positive. And so the solution the system finds to minimize the energy is to arrange the phase in this Mercedes-Benz, let's say, configuration. Since the chirality, the possible chiralities are two, then choosing one of the two will spontaneously break time reversal symmetry. So this is essentially the reason why you have this dome. But then the question we try to address is to look around the peak of this dome to see if there was some additional phase emerging for this range of temperature and doping. And actually, these are the results. So as you can see, in between a low temperature phase where the system is superconducting with a Meissner effect signaled by the onset of a diamagnetic response, and a high temperature phase where essentially the system is in a metallic phase, there is an intermediate phase where the system shows an anomalous response in the specific heat. It is still resistive, but most importantly, it shows a very pronounced spontaneous Nernst effect, which essentially signals the presence of spontaneous magnetic fields in the system, and the fact that above in this temperature range, so above the superconducting critical temperature, the time reversal symmetry is still broken. So the scenario is compatible with the presence of this fermion quadrupling condensate appearing above the superconducting critical temperature, where again the order is in the phase difference. And this is the phase diagram also at the finite magnetic field. Just to show you, there have been also other measurements, muon spin, ultrasounds. More recently, there have been also the detection of two peaks in the specific heat associated with the two critical temperature. There have been the observation of metastable fractional vortices compatible with this picture, and even more recently, the observation of a fractionalization of these vortices via scanning tunneling microscopy. From a theoretical point of view, the standard model I showed you before, so this Gisborne-Landau model with three-band and Josephson frustration, is not enough to account for this phase at zero magnetic field. So what we did has been to consider an additional term, which is this term here. It's a current interaction term, which is also known as Andreev-Bashkin interaction. Is essentially a dissipationless drag between the two components, which actually, you see, leads to the splitting of the two critical temperature, and even in the extreme type 2 case. So even in the phase where it's harder, let's say, to split these two critical temperatures. So this is just to conclude the motivational part. So the more details on these theoretical studies can be found in this paper. So I've shown you that so far this kind of fermion quadruplet condensate have been observed just in this iron-based superconductor. Recently, there have been some claim of charge 4e superconducting state in Kagome superconductor with this ring-shaped geometry that still need to be, let's say, assessed. And even more recently, there has been the first experimental observation of the prediction by Boris and Anatoly on the presence of a counterflow superfluid, which is essentially an higher order condensate of bosons rather than fermions. So this is just to say that essentially, despite the massive theoretical effort, so far there are very few experimental observations of this state. And this actually motivated us to look to a different system that is magic angle twisted bilayer graphene. We are aware that this system already hosts a lot of phases. But we were interested in this essentially for two reasons. Because it's a two-dimensional system, so the phase fluctuations are important and are much stronger than in 3D case. And it is a single band superconductor with a multi-component nature, so an unconventional pairing. And these are, let's say, the key ingredients we need to try to look for this phase. So what we did has been to start from a paper published by Ciccinazze, Klassen, and Chubokov, where they essentially looked at what could be the ground state at all feeding, and they found via some ERG calculation that most, let's say, likely pairing form is of this form. So it's a this plus ID, meaning that essentially the superconducting order parameter has a two-dimensional irreducible representation with this key intercomponent coupling. So what we did has been to start exactly from this model. So this is the Gisborne-Landau free energy. This is the Landau, the key, let's say, intercomponent potential that we parameterize in terms of these two phases, essentially, where gamma model the relative amplitude between the two components, and phi1 minus phi2 is the relative phase. So we study the model in the approximation where the total density is constant and equal to 1, while retaining the relative amplitude fluctuations and, of course, all the phase fluctuations. So this model is particularly interesting because depending on the sign of K, it has two different ground states. So for K larger than 0, the ground state is a superconductor that spontaneously breaks time reversal symmetry. For K smaller than 0, there is an accidental degeneracy that can be lifted once considering higher order terms. The system has a nematic superconducting ground state. So in the present talk, I will just focus on this case here. But we are currently working also on this other case. I don't know how much time is left. Okay. So what we did has been to perform a large-scale Monte Carlo simulation on this model in the limit of the superfluid limit, essentially. So in the limit of infinite London penetration length, and again, fixed total density of the two condensate. The system, as already mentioned, this zeta2 symmetry associated with the phase difference, and then we have the superconducting modes that in this case undergoes a BKT phase transition because we are in two dimensions. So now the game is essentially to understand in which scenarios we will end. So if we have just a single phase transition or two different phase transition. And the major role is played by this topological object. So which would be the first proliferating, triggering one phase transition rather than the other. This is let's say a non-trivial problem, especially because let's say easy and simple energy estimates can drive you to wrong conclusion, because very often the proliferation of one kind of topological defect can trigger the proliferation of one other kind and induce a preemptive first order transition. So the emergence of these phases is actually not, it's a delicate issue, so one has to be careful on this aspect. And Monte Carlo simulation is a good tool because it takes into account all the possible interaction between these defects for free, in the sense it's already embedded in the method. So what we did has been to essentially look at the zeta 2 phase transition by measuring this sort of Ising magnetization associated with the two possible chiralities, and from which we then computed the Binder coolant. And for the superfluid superconducting phase transition, we computed the superfluid stiffness, so the Licity modulus sum, that essentially measure how rigid is the phase sum phase with respect to external, let's say, field. And via a finite size scaling, we extracted the two critical temperatures. So this is for the case k equal to 5. And as you can see, we could quite well resolve the two crossing points that appear to be well separated for this case, in particular with the superconducting critical temperature being smaller than the zeta 2 one. What actually surprised us is that when we explore other value of k, which is our model parameter, essentially we could resolve a splitting of the two critical temperature for all the values of the k we have investigated. This essentially means that in this model, the two critical temperature, are always separated, and then this fermion quadrupling condensate seems to appear quite generically in the system. This is again a phase that is non-superconducting, but maintains order in the phase difference. And this is quite different from previous works, where actually this phase could be found only for very large value of this Josephson coupling. This was a slightly different model with 3-band and phase frustration and without relative amplitude fluctuation. So they could find a splitting just for very large value of G. So essentially this suggests that this is a very promising model for looking at this phase. So regardless of magic angle twisted bilayer graphene, any system that can be described by this model could be a very promising system for investigating and look at this phase. Of course, we have still many questions open. In particular, we would like to understand better why this is always the case, why the splitting occurs always in this direction for these parameters we investigated, and what happens in the limit that k that goes to 0, where essentially the system is supersymmetric and there are no phase transitions. So here, what we found with Monte Carlo is that the finite size scaling are very pronounced, and then we would like to investigate the problem with some other mean. In particular, we are working to some ERG approach to look at the model in the thermodynamic limit. And with this, I think my time is almost done, so I will just conclude. So I hope to have raised some interest in this fermion quadrupling condensate that now has been observed experimentally. So I think maybe there is an extra motivation to look for it in real materials. And of course, what we are now trying to understand is how to engineer the emergence of this phase, understanding which are the key mechanisms, and how can we tune specifically the topological excitation of the phase in order to trigger the emergence of this phase. And yeah, with this, I just thank you for your attention. Thank you. Any questions?
So your simulations were done in the direct space, empty,
Yes.
not using duality.
No. That's it.
Can something like this be realized with ultra cold atoms, or do you need to have charge systems?
No, exactly. With ultra cold atoms, you can have, I mean, it depends on how you prepare the system. But of course, for instance, the experimental observation of this super counterfluid was done exactly with ultra cold atoms in development. So now one can, yeah, play around them. To look at the Fermionic case and yeah.
Other questions? And let's thank our speaker again. Speaker. Which what?
Which microphone using?
I think we have, yeah, you use your own, I think. Yes, if the comment about the focus was about the camera focus, I don't think we can change that. But the slide should be in focus. I think there's an app for this camera where you can change focus, but I don't know who it's.
This.
Let's see. Okay, and if there's a sound issue, please unmute and complete.
All right, okay, so I'm going to talk on pole representations and analytic continuation of Green's functions, but more generally, pole representations and then analytic continuation as one of the applications. This is work that has been done mostly by one of my graduate students, Lei Zhang, and codes and theory can be accessed with these links. So imagine yourself as, your own graduate student. Here's a correlation function. At great pains, you extracted this from some horribly expensive Monte Carlo simulation. And of course, your advisor asked you to give the spectral function, right? And so, you run some analytic continuation code, you come back proudly with something like this. It has a couple of bumps, maybe a gap somewhere in here. And that's where the questions start, right? You believe it. Which features should you trust here? Can you exclude a certain scenario? For example, think your satellite peaks, right? Some peak after peak phenomenon or so. Or worse than that is I expect to see a bump over here. Can you give me a spectrum that has the right bump at the right place? And of course, that's a difficult question. So this talk is about analyzing spectral functions and Green's functions, putting the analytic continuation problem onto a rigorous mathematical footing, then talking about control and systematics, what it means to actually get better continuations and whether we can get better continuations for better data, and also a quantum information approach for that type of problem. And I don't think we have time to talk about denoising and extension problems. All right, none of this, even though it looks very mathematical, is difficult in any way. It's mostly mathematics from the 1920s. All of this is coded up in codes that are about 4 pages of Python long. There are complicated codes in my group, but these are not amongst them. So anytime you have a spectral function, feel free to have a look at these repositories here that have actually these implementations, and have a look at whether this might be useful for you. So I will mostly limit the discussion to positive fermion spectral functions, but there are generalizations for bosons, anomalous, matrix solid, and so on extensions that we can also discuss. All right, so let's talk a little bit about these spectral functions. You know, the standard problem that you have is out of some Monte Carlo code or, you know, semi-analytic code comes a Green's function, Matsubara Green's function obtained the imaginary frequency. You're really interested in the real frequency Green's function, in particular in its imaginary part. If you look at that function, it is related to the Matsubara Green's function with this integral kernel. The spectral function is then just -1/pi the imaginary part of Green's function. And so in principle, you could take the equation that you have over here, write it as a, you know, kernel equation, just invert the integral kernel, and you're done. And, you know, mathematically that's correct, but really very little progress can be made with this approach if your data is noisy. However, when the data is accurate, there's a rigorous mathematical framework to discuss these. This is what it means. You have this ill-conditioned problem over here. What you see here is the band structure of silicon, obtained in this case on the Matsubara axis in a fully self-consistent, you know, RPA or GW approximation. You know that silicon has an indirect band gap. You can sort of see it here, right? You know that there are bands in this problem, but they're really fuzzy. They're sort of washed out. And that is the consequence of the ill-defined or ill-conditioned nature of the analytic configuration. So that's our starting point. This, by the way, is just standard maximum entropy with standard parameters. So I'm going to take a step back and look at the Lehmann representation of the Green's function, written here as, you know, a 1/the partition function, the sum over all of my indices in Fock space, you know, some matrix element squared, some exponential decay summed up, and then an NSG denominator. And if you look at this term, that term, and the partition function over here, you see that all of these terms are positive, meaning that if we look at this function in the upper half of the complex plane, where z as x plus iy and y being positive, then the imaginary part of the Green's function in the upper half of the complex plane, as you can easily convince yourself, because this here is positive, this is positive, and that is positive, is strictly negative for all values. And therefore, for any Green's function independent of the system that you're studying, the analytic properties imply that its imaginary part is smaller or equal to 0 in the upper half of the complex plane. So why bother, right? I mean, cool, but is this actually useful? And is this actually useful in the 21st century? Well, it turns out that functions like that have been studied in complex analysis back in the 19-teens and 1920s. They're so important in measure theory, they have their own name. They're called Neven-Lina functions. And so functions with a positive, actually, imaginary part in the upper half of the complex plane are Neven-Lina functions. And Neven-Lina functions can be mapped onto Schur functions. Schur is the group theory Schur here. Basically, by mapping the upper half of the complex plane onto the interior of the unit circle here, or onto the unit disk. And every Schur function, as Schur proved back in 1916, has a continued fraction expansion that can be recursively defined. And that continued fraction expansion corresponds to a Paul representation. There's actually a 1917 algorithm given by Schur that tells you that if you give me a bunch of points inside of the unit circle, I will give you not just one analytic continuation of your Green's function, I'll give you all possible analytic continuations of the Green's function. And of course, once I have that, I need to impose an arbitrary regularization criterion to then pick the best one in that function space that I want to look at. And so in practice, if we have clean data, we can take this sort of prescription with the analytic properties and a complex mapping over here to obtain these contractive functions, and from those obtain all possible analytically continued Green's functions. Why is this a good approach? Well, as I said, these functions have been studied quite a bit. One of the people that was studying this was Georg Pick, and he was actually studying the existence problem of these interpolants. So under which conditions can you even have a causal Green's function that has the right analytic properties? And he said that if you have a Green's function and you evaluate it at Matsubara frequency I, and you get, you know, g of xi is, or g of omega I is yi here, then what you should do is you should build the Pick matrix. The pit matrix is 1 minus Green's function at point I times Green's function at point J complex conjugate divided by 1 minus Matsubara frequency I times Matsubara frequency J complex conjugate. Build that matrix, diagonalize that matrix. It ought to be positive semi-definite, so you're not going to find any negative eigenvalues. And you know that if you just take a random set of points in a complex plane and you start building matrices and diagonalizing them, you're going to get about as many positive as negative eigenvalues. So what you see here is that the function space of legal Green's functions is actually very, very constrained. And now all of a sudden, we don't have an ill-conditioned problem that is very, very sort of arbitrary and difficult to solve, but we actually have a very constrained problem right here. And that is what this allows us to make quite a bit of progress. Now in practice, this here is a complex analysis criterion, works in infinite precision. If we have Monte Carlo data, almost never are our data causal. Even if we have semi-analytic data like GW, known to 14 or so digits, typically the big criterion is violated on that limit. But very often, even then, we can make progress and look at analytic continuations. This here is this Schur interpolation method applied to the analytic continuation problem that I had over here. This is the same data that you just saw before. And you can see that now this problem is so well constrained that we can actually see the different bands. We can see the degeneracies, the triple degeneracy at the gamma point. We can see the indirect backups. And, for every energy, we see a couple of bands until then finally, in this formalism, we are about to lose resolution. And so that was really a big breakthrough on the in the field of sort of error-free finite temperature field theories, your GW, your vertex-directed GW type of theories, where we really now can do math on the Matsubara space and then analyze spectral functions in the real frequency space. This here is a conference where we're not really talking about those types of methods, but many of us are working with noisy data, with Monte Carlo data that is, intrinsically polluted on the level of, typically somewhere between 10 to the minus 3 and 10 to the minus 6. And so complex analysis as a framework is not as useful as it is for noiseless data, because in complex analysis, if I wiggle a little bit over here, my function's going to change everywhere, right? And so while the Nevanlinna framework is very useful for discussing the mathematical sort of setup of these problems and all possible function space functions that are in a function space that are actually solution to the interpolation problem, we really need something different. We don't need an interpolation. We need an approximation, and ideally an approximation that is controlled in the sense that we have a small parameter that as our Green's function becomes more and more precise, we can get better and better analytic continuation. Now, traditionally, we've done that with maximum entropy, right? We've obtained some data, we've had some error bar, and then we had said, well, let's do some least square fit to our Green's function in such a way that out of all possible functions, we're getting the ones that are the smoothest. Now, this is usually formulated in a language with default models where you trade the precision of a fit with the deviation from a default model. You arbitrarily then set a temperature that biases you towards smoother models or more precise fits. But the regularization in this type is really a smoothness of a function. My claim here, and that's really sort of the premise of this talk, is that this is not a good way of thinking about typical Green's functions. Because if you've ever looked at a Green's function, here is one, right? This is not a smooth function. So we need a different way of picking in our function space those types of Green's functions that we actually care about. Smoothness is not good. And what I advocate here is that we should talk about information content in those functions. Out of all the possible functions, I would like to have those that have the least possible information that are still consistent with the spectral functions that I have. And for that, I want to go back to my Nevanlinna framework, and in particular to Isai Schur, 1917, who said that every Schur function has a continued fraction expansion. Every continued fraction expansion can be written as a pole expansion. And so let's just look at those pole expansions and let us find the pole expansion with the fewest poles that is consistent with both the data and the analytical properties of the function that we care about. Here's a pole expansion or a pole representation, right? It looks something like this: AL over Z minus psi L. AL is a complex weight or a complex prefactor. Psi L is a residue, right? Psi L is a pole location. Z is a variable anywhere in the complex plane. And it is our task to approximate a function, for example, on the Matsubara axis or on the real axis, as precisely as prescribed, with a minimal number of poles here, M, that are of that form. You provide to me your Green's function at point Z in the upper half of the complex plane, together with a tolerance. You believe that your data is accurate to 10 to the minus 5. And I then will give you an algorithm that is needed to construct the minimal number of poles in that data and the corresponding pole locations and weights. Now, it turns out that problem is actually well known. This is a problem related to a signal processing problem that comes from 1996, from Daskar-20, where this type of fit, which is an approximation of a function with a set of exponentially decaying oscillatory function, was discussed. The Crony interpolation problem, so the solution of this problem that you see over here is very, very badly defined, is very ill-defined. However, the Crony approximation problem, where you find the number of poles that are consistent with your data to within epsilon, is actually a stable interpolation problem that we can solve. And so, let me talk a little bit more about those spectral functions. What I have here are, two of the spectral functions that we know and love. One is a two-dimensional square lattice type binding density of states. The other one is a semicircular density of states. You can see that this one is difficult because it has a band edge over here, and it has a Van Hoff singularity over here. That one is actually difficult because you have a square root singularity and a branch cut in the lower half of the complex plane that generates that sort of non-analytic behavior. So if I say, well, I have a precision of 10 to the minus 2, how many poles do I actually need of that form here to represent that function on the real axis with those poles? And it turns out with 9 poles, I can give you an accuracy of 10 to the minus 2 at the sampling points. The sampling points exclude the divergence at 0. And here with 5 poles, I can give you an approximation to the level of 10 to the minus 2. As I increase my error tolerance, by the time I'm at 10 to the minus 4, I need 17 poles over here and 11 over there. If I want to approximate this to the level of 10 to the minus 6, I need 21 over here and 13 over there, right? And as we now ramp this up, I think I have 10 to the minus 8. I need 7 poles over here and 10 to the minus 7, 24. Here we go, 28 poles for 10 to the minus 12, and so on. So I can systematically make this more and more precise. What do these functions actually look like? Well, this here sort of looks like a Lorentzian. And indeed, if A was real, this would just be a Lorentzian somewhere in the lower half of the complex plane. Because A is actually complex, these are anti-Lorentzians that then can cancel the long tails of Lorentzians. And here you see the semicircular density of states approximated to 10 to the minus 2 with 5 functions. Those 5 functions are defined by poles in the complex plane over here, right? The real axis is right over here, and generate on the real axis these red curves here. And so the sum of the red curves is precisely the black curve. So pole expansions are a very systematic and very efficient way, a low information way of representing continuous functions on the real axis, or approximating continuous functions on the real axis. And basically, all we need to do now is find a clever way of actually constructing the pole expansion. So for now, give me, assume that I can construct exponential approximations of that type. Given a function, g, sampled uniformly on a grid, I can then construct a set of weights and oscillatory exponential functions, wi, gamma I to the k, such that that sum here will be smaller than epsilon for all of the sampling points on which I know that function. If I can do that, I can then have a smooth approximate of my sampled function. The exponential function that I have over here, gamma I to the k, has all of its poles far away from my interpolation interval. So this is a function that doesn't wiggle in between. It's actually very, very smooth. The moment I have an approximation on the line, I can go back to my complex analysis course and look at the Zhukovsky transform. What the Zhukovsky transform is doing is it's taking an interval on a line, taking your hands, grabbing in there, taking the entire complex plane, morphing it around, putting the line that you had onto the unit circle, and mapping the rest of the complex plane into the interior of the unit circle. As part of the scheme, if my line was here on the imaginary axis, as I would typically do it in the analytic configuration problem, all of my poles on the real axis will end up in the interior here of this. On the real, or my real axis will be the black line. My poles below the real axis here will be in the interior of this X-shaped regime, so they will be actually fairly close, towards zero in the unit circle. So the Zhukovsky transform here maps the real axis onto this X-shaped region, and the map maps the poles close to the zero of the new unit. Yeah.
So what kind of data do you need? So basically, what do you assume about the function? Ignore physics. Like, what do you need for this construction to be true?
For this construction, you can give me an arbitrary set of G's, and I'll give you a set of omega i's, gamma i's, and k's that approximate us within epsilon. If you give me a low rank G, my k here will be very small. If you give me this,
low rank, what does it mean?
Smooth. For now. I'll get back to that. I'll show you a couple examples in a second, so that will hopefully get clear. But just humor me for a moment, right? Because we now have a good interpolant here on the unit circle, and the moment we have that, we can compute the moments of that function by just numerical integration. And then, according to the residual theorem, you know that this is just the poles times the pole strength for the residues times the pole location to the power of k. And if you look at that function over here, that looks precisely like the Prony problem that we just solved. So if we know how to solve a Prony problem, we can solve the Prony problem again and obtain the map poles and weights in the unit circle, apply the inverse Zhukovsky transform, and now we get the poles and the pole weights in the original complex plan. And so that will give us access to the pole locations in the poles. What I haven't talked about so far is how you actually solve the Prony problem. So this is the problem that we need to solve. And it is actually a phased array radar or synthetic aperture radar problem, direction of arrival problem that comes originally from acoustics, and is really one of the fundamental algorithms of signal processing. And so here we have a lot of different numerically stable algorithms, most famously the matrix pencil method and Esprit. And what we're actually doing is using the Esprit. So what that does is it takes that matrix of moments, it builds a Hankel matrix of so-called Hamburger moments out of that matrix. Then it uses a singular value decomposition to obtain the singular values of that Hankel matrix, which is then truncated on the level of epsilon, that is your error tolerance. And in this way, we have full control over the physics of this problem. As we're decreasing the epsilon, we will have to keep more and more of the singular values of that problem. And with that, we'll have to keep more and more of the poles. The pole weights are then extracted with a Vandermonde system to obtain the coefficients.
Excuse me.
Yeah.
Just to understand, when you go for larger number of poles, the previous poles remain, or they completely move from the original?
That is very interesting. What I assumed was that the previous poles would just move all over the place. In fact, they move a little bit, right? But basically they stay the same. And I'll give you a better, I think I may have an illustration. Well, let me come back to that, and otherwise I'll show you some data. It's actually very interesting. It really means that you found the poles that give the main features. And as you get additional poles, the weights of the additional poles will be very, very small. You'll basically just twiddle your function a little bit to adjust it, sort of to fine correct that. All right, well, so back to that, how does it actually work in practice? Here you have two Lorentzians a little bit broadened, basically delta peaks. Well, your algorithm, if you have an error of 10 to the minus 4, says you have 2 delta peaks. And if you look at the error of that, which is the integral of the absolute value of the difference of the continued and the original spectral function, you get some value which is not very good. But as you then make your data more and more precise, the algorithm says, well, you have two Lorentzians, and you keep having two Lorentzians. And more importantly, the error of the integrated error of the difference here, exponentially drops as you're ramping down the error that you have in your original data. That in a way is trivial. This is clearly a very low information signal. You just had two poles. On the other hand, if you're in condensed matter, then you talk about quasi-particles all the time, and just even one of those is your quasi-particle, right? So this is really very good at resolving those low information features. Here, this here is a 3-peak spectrum, and at the very lowest level here, you will have to have 3 peaks to model the 3-peak spectrum. These are actually Gaussians. So the Gaussians are now approximated by Lorentzians, and you can imagine that actually, they have the different asymptotic behavior and so on. So that actually takes quite a bit of poles. So as we ramp down our epsilon, you can see we need 3, 4, 5, 8, 9, eventually 11 poles to accurately represent that spectral function. But the important thing here is that we now can make these approximations systematically better. So here is how you would look at, a triangular lattice density of states, a semicircular. I think this is some frustrated triangular lattice. This is some, condo-like feature that you have here. Now, if you plug these into standard analytic continuation methods, we have totally overfitted this over here to make it look as good as possible. You see that, well, there are these spurious oscillations, you're not getting the band edges right. The square root singularity here is totally gone. The second peak that you get after the first peak is sort of totally washed out. So these are really the limitations that you have with the traditional methods. As we're now going, and ramping this up on with the Prony approximations, you can see that, you're still not perfect here, but for most of the time, you're actually capturing this. You're capturing the divergence here, you're capturing the band edge, you're capturing the square root singularity, you're capturing a second peak after the first peak. You're actually not capturing that little foot that then drops down. That's washed out, it's captured only in one single peak. And condo problems like this are actually very, very easy to represent with just a very, very sharp quasi-particle that is close to 0. Let's see. Why don't you want to go? All right. None of this, by the way, enforces that we have fermionic relations. We can put this into the Hamburger moment problem when we solve it, but we don't have to. So we can straightforwardly apply this to off-diagonal fermion, matrix valued problem, discrete problems that are really consisting of delta function poles, where we can also enforce that our poles are on the real axis, bosonic problems, off-diagonal bosonic discrete problems, and so on. So you can mix and match these things at will. We can do this representation in terms of a matrix valued form, where this AL is a positive semi-definite matrix valued function, and the psi L's are shared poles between different parts of my Green's function. And now here, for example, you see a sort of 3-peak structure in the diagonal part, an anti-symmetric structure in the off-diagonal part, and a set of shared poles here that generate this structure here on this. I think it's like 5 or 7 poles on the real axis. I'm basically out of time. What I want to show you here also is that, first of all, these Prony methods we can make arbitrarily exact if we ramp up the number of input or the precision of our input data, provided that our data is well approximated by a low rank, or a low pole approximation. And it just so turns out that the typical way that we talk about our spectral function is in, bump over here, peak over there, sharp features over here. Those are poles, right? These terms are well captured by the individual poles that we have. So the typical spectral functions that we talk about are not random functions that you wanted to plug in there. It's going to work for these too, right? But if you want to have a low rank approximation, right, it's going to be, some sort of smooth function that has, has a few poles in a complex plane. Anyway, right, so you can see that this converges here exponentially, whereas with the typical smoothness regularization that we have, we're really not getting better as we make our input data better. And that is the big drawback. That's why analytic continuation really couldn't make any progress with the standard regularization criteria. Anyway, I'm out of time. So I would say try it. If you do want to try it, pip install our code. Find it on the Green Software homepage. That's our open source package. All of this is MIT licensed open source. So if you want to, you can download our code and sell it. You know, other than that, ask us for help and we'll help you get started with all of this. Thank you very much.
Sorry for a naive question, but for me it looks a little bit similar to Padé approximation.
Yes.
So can you comment on?
Okay, so this totally is a Padé approximate, right? It's a continued fraction expansion or a pole expansion of a function. Now, we know that any measure has a Neven-Linna representation. It's actually unique. So any spectral function that you have has a Padé approximant of this type, right? When you typically construct a Padé approximant, what you do is you choose the number of poles on the numerator, number of poles in the denominator. You know, one is one higher than the other ones to get the right high frequency behavior. But that's an input, and it's usually given by the number of points that you interpolate through. This here is different. It's not an interpolation, it's a fit. It enforces the right analytic behavior, and it adaptively chooses the fewest number of poles that you need to get that. Now, when you were running Padé, you know, it sort of looked okay at low frequencies, and then you would do this here, right? And the reason for that is that you had two poles that, you know, didn't have to be there, that were very close to the real axis and almost canceling each other. Now, those two poles in this type of expansion, right, they cost. If I can get away without having those two poles, I will try to do that. And that's why you're not finding these types of high frequency oscillations. You're finding a very sort of regular functions here. The other thing is that usually in Padé, you will find poles in the wrong part of the complex plane, right? Which is not the case here.
More questions? Yes.
What if you try this on some function with not at all like a delta function?
Well, the imaginary part of the real frequency self-energy, you know, up to the scaling factor has the right Neven-Linna properties, right? So self-energies are Neven-Linna functions. And in fact, I don't have this in this, yeah, I don't think I have this in this talk here. But you know, the same example that I showed you with Neven-Linna interpolation for the silicon example, that is what we're now typically doing for the real material self-energies with the matrix valued, here the matrix valued Prony or Esprit method to get the self-energy approximated. So yes, it doesn't look like a like a set of delta functions at all, but you know, neither does this here, right? It still has a low rank pole approximation. And this just finds that low rank approximation.
I've never heard this word Neven-Linna. So is it in physics terms equivalent to being retarded Green's function, or it's something more sophisticated? So is it just a statement that, you know, real part, measuring part is positive and that's that, or
I mean, the term, or why did the mathematician put a term to these functions?
No, I mean, what is that?
So
is the statement is positive and that's what it means, and you just call it Neven-Linna now? It's something more than that.
I would say that, you know, there's an entire literature of measure theory and Neven-Linna theory in mathematics. So if you Google the term, you'll find all sorts of math papers on those subjects. Typically, the reason why they bother is because there's a one-to-one correspondence between a measure, you know, think of the derivative of that as the spectral function, and Neven-Linna functions, right? So there's a Neven-Linna function for any measure. And it's typically much easier to work with the Neven-Linna functions than with, you know, functions on the real axis. It's basically an extension of these functions into the complex plane that has the right analytic properties. So no poles in the upper half of the complex plane and everything in the lower half of the complex plane.
No, I mean, I'm more asking like not why they care about this function, but
Yeah.
why you care about this function.
Regarded
Green's function or something.
So yeah, exactly. Retarded Green's functions, self-energies, hybridization functions, right? All of these have the same analytic properties, right? And so I'm not smart enough to go and develop this mathematics myself. So I look up the Neven-Linna theory and Neven-Linna textbooks that they wrote in the 1920s, where they actually did all of this for me. So that's why Neven-Linna is useful.
That's okay, let's.
So, I mean, this might also be naive, but I think for me, this Prony problem that you are solving here, that is the analytic continuation problem, right? That is just in imaginary time, I have a bunch of superpositions of decaying exponentials, and now you want to fit them. So naively, I would think that at least this sort of least square fitting, this is a super ill-conditioned problem because I have to invert this Hankel matrix, which is essentially singular. So the thing I didn't get is basically, why is it now gone? Like, why is it? Because that is the problem. No?
Not quite. So let's look at what the Prony problem actually looks like, right? So this is the Prony problem,
Right.
right? This is your data.
Right.
But this here is not in the form of a pole approximation. Right?
No,
I mean, right. So getting from this smooth interpolant on the real axis to a pole approximation, that's quite some steps.
Yeah, there's
Right.
a lot of stuff that goes in
Right.
that, but I would say this problem is still conditioned.
No, I mean, this is an approximation problem. What
Which
you
is
mean
ill-conditioned.
is that, I think when you say ill-conditioned, what you mean is that you can get away with very few Ks up here to approximate this here to within epsilon.
Right.
Right.
Yeah. Or
And-
if I had too many Ks, then actually there would be many gammas, which would give you the same epsilon.
But that's not the problem, right? That was the original Prony interpolation problem.
Right.
And that one is really, really badly conditioned,
Exactly.
right? So how do you regularize this? How do you get the minimum number of poles, the minimum information in your Green's function that you must have? And the way that this works is you don't just give me your data, you give me the epsilon. And I can guarantee you that the K that I give you here is the minimal K that is needed to approximate this to within epsilon.
Right. But
And
so the
now you
key
regularize it.
regularization is that you want the minimal number of poles.
Yeah.
Right.
Yeah. You know, and we can agree or disagree whether that's
Yeah.
a sensible thing, but it works really well for the typical things that we're working with.
Just, I have kind of a foundational question regarding that. And it sort of ties in with the work we did on the Polaron spectral function, where we did have this challenge that we had very different spectra that were consistent with the Green's function data. So let's say I have Green's function data with 10⁻⁶ accuracy, and I have two qualitatively different Green's functions that are consistent with it. How can I find the criterion to distinguish between them without invoking some external physical principle? Or in other words, if, for instance, if then I went ahead and had 10⁻⁻12 accuracy Green's function data, presumably it would exclude one of the two, or maybe even smaller error bars. So how, I guess just from the foundational perspective, what makes this distinction, or is it just something that happens to work in many cases?
No, I would say, you know, we have to regularize this problem. We have to impose a criterion that says we like these types of Green's functions better than those types. And my criterion is the fewer wiggles it has, or the fewer, sorry, I should say that the less information that it has in terms of poles, right? The better it is. That is arbitrary, but that's how I choose to regularize this. You know, it seems to work, right? It seems to work for most, or it seems to produce, you know, the ones that we want. You can construct Green's functions that, you know, have, you know, some peak far out that are very, very difficult to resolve in this way because, you know, you're happy with just putting a Lorentzian out there. Nothing I can do about that, right? This is a very large function space, right? I think what we've learned with this is that smoothness is not a good optimality criterion. You should
Right.
get rid of that.
No, yeah, I mean, that's. So essentially it works very well for the physical system, for Green's functions that occur in physical systems. So it
Exactly.
seems to be.
Right.
pretty
And of course, once you have a pole representation, you can do all sorts of things. You can do analytic integrals, right? You can do residue theorems. You can multiply these things. You can do diagrammatics. It's sort of, and you can talk to your theorist friends because a quasi-particle actually has meaning here. It's right there. You know, there are two numbers for the weight and two numbers for the pole. And so that actually is quite a, it brings this a little bit away from just number crunching and really puts it into a language where we can talk to the theorists.
Okay,
Maybe one more question. Suppose you want to approximate in this way a function which actually has a branch cut in a proper plane. How will this?
There's your branch cut right here. So you see this square root density of states actually in the branch cut in a complex plane, it goes, goes along here. How well does it work? Well, you should have an infinite number of poles, but to within that precision, you can sort of model this branch cut with a set of, in this case, 5 discrete poles that actually lie precisely on that branch cut. As you ramp this up, I think I don't have the plot here, right? As you ramp this up and you have 28 poles, the 28 poles are modeling your branch cut bit by bit by bit. So just by looking at it, you know that there's a branch cut right there, right? But you only have, you have finite precision for your data. So the code will tell you you can get away with a finite set of discretized poles rather than a branch
That's what
cut.
I wanted to hear from you, that if you have something more than just simple poles, then your approximations will these poles will condense on this
Exactly, and it's actually very beautiful. So as you ramp up your precision, so you don't have to talk about the analytic continuation problem for this. This is really the representation problem, which you're seeing here, right? And you can see that as you increase the precision, and you have to work harder and harder to get this branch cut here to work, the edge to work, right? It will really put those poles right where they should be in the continuum space.
Okay, let's thank the speaker again and continue with call. So Johan and I start at the same time for dynamics. Because I was hoping to see on the south. It was in Sweden, but it was when everybody was in the summer, in the summer.
Oh, but then was certain.
That's good news. Thanks.
Yeah, it was good. He told me
Yeah, yeah, because it is about, those are good times.
So you like when you there and then
Yeah.
stay there. Then when you think about
I don't know different units. Yeah, they're that one. I was a bit. Then I did another folder. Backwards job.
okay.
Around neighbors. Yeah, no, very cool. And you go by this, and I just started. Yeah, but he already kind of time. And I think I was in his office and he left. But then eventually they kicked me out because I said I can. And then you came, yeah.
Yeah, no, so the,
I know the others before. I don't know when the.
yeah, I did that. Yeah. Yeah. We are still working on this project and actually we only started.
High frequency.
Yeah, it's a very big pedal to, yeah, it's very.
You are always maybe with new projects.
Yeah.
Yeah.
How it goes, yeah.
So, yeah.
Yeah, I don't know much about models of actual real estate.
Okay, yeah.
Minus the.
Compound, but there are some fundamental theoretical questions that are there. So when I was discussing with that before, for instance, we don't know exactly what to expect when
Pure math.
And yeah, and I would like to do this painting. So,
Never done reading for me. And just
It's a big step here. So mostly what I do is move it out. Related so purely is family gases. So we have a so that's the whole. But kind of very simple. Started then, but then with diagrammatics. It's possible, yeah. That's, yeah, so that was so fun to see, but kind of my big dream is to do generally equilibrium and time decline physics for organic systems and apply in terms of purity systems, maybe family gas, because that's like a big develop some new methods. Yeah, that's why I'm really curious about these tensor methods. Yeah, a lot of things. Should make me this one before.
The Russians are still hanging out.
I derived the solution for between our notation, so for the screen. So that.
I guess I should unmute this or this, oh no, this already happened. So yeah, I think with this, let's try to start more or less on 1 minute left. So it's my pleasure here. Avishkar will talk to us about strange metals and his work with Peter and Mike.
For the explanation. So, yeah, I'll be presenting some results from quantum Monte Carlo work on like models with spatially random interactions in 2 dimensions that can lead to strange metal behavior. You know, this quantum Monte Carlo work is part of an extension of a bunch of theoretical work I was doing earlier with these same kind of models. So, yeah, just a quick overview of strange metals is they're metallic phases of matter that occur in strongly correlated 2D or layered materials like cuprates. And their hallmark feature is they have a linear electrical resistivity down to very low temperatures, as long as you suppress any superconductivity. And sometimes they're deemed to be proximate to some putative quantum critical points, although that is not really well established, in my opinion. And in fact, the model that I will show doesn't really have quantum criticality. So the transport, so this DC resistivity and linear T resistivity is a transport problem. And so in conventional metals and electrical transport, this looks like something like this. You have a residual resistivity, and then at low temperatures, you have a T-square correction from Vin-Club processes in Fermi liquids. And then high enough temperatures, you get T-linear behavior from Lagrangian or by phonon mechanisms. But the important thing is it's not linear down to zero temperature. Whereas in strange metals, it's linear down to zero temperature. So, so that requires to have a finite linear resistivity. It requires some momentum relaxation process that can give rise to linear resistivity at low temperatures. And the three generic options in solids are Umklapp, phonons, and disorder. But at low temperatures, phonons, they're gapped out. Umklapp is also T square. It's also can be described in terms of gap boson. So like none of these naively lead to T-linear resistivity. And another feature of the strange metals is that if you look at the AC transport, it has a optical scattering rate.
Why for phonons you need finite optimization energy?
Well, it's the Bloch-Bruneisen energy is like Vs times 2kF, and the Fermi surface is large. So that gives a.
But you can have small angle scattering.
Small angle scattering doesn't relax current.
Well, eventually it does, so it just longer for time. I mean, okay.
So it's so we also have this optical scattering rate that is linear in frequency, and that is definitely an elastic mechanism. We come out from phonons in the regime in which they are elastic and give linear resistivity, and also can't come out of like your usual impurity potential disorder, which is also elastic scattering. So the resolution that we have been thinking about for some years is that the electrons have disordered interactions. The interactions are spatially homogeneous. These can give you both momentum relaxation as well as inelastic scattering simultaneously, even in the low temperature limit. And then you can have some chance of explaining like these features. So there is like evidence that there is disorder in electron interactions in some of these materials like the cuprates. So for instance, it's been noted in some experiments that there is inhomogeneity in the charge density wave order. So there are regions where have charge density wave order and other regions where you don't, and that's correlated with like the inhomogeneous distribution of the oxygen dopants in this compound. And if you think about the charge density wave order as a field theory language, then this would mean that some regimes it's ordered and some other regions it's not, and that would be disordered by the mass parameter of that field, and that also means that there's disorder in the strength of the effective interactions that lead to charge density wave formation. So along that line of thinking, there is previous work that we have done in which we consider like your Fermi surface coupled to like a critical field theory with a spatially random interaction. So you have a random component, Yukawa coupling, and that that modifies like at the mean field level or Hertz-Millis level, it modifies like the low energy Landau damping structure of the boson as well as the fermion self energy, and you get like this omega log omega marginal Fermi liquid self energies. And importantly, since this that's only 2 dimensions, of course. And importantly, since this Yukawa coupling is disordered, it relaxes momentum and also easily leads to large angle scattering of fermions by near critical bosonic modes. So the marginal Fermi liquid self-energy also shows up in the transport properties. You get like a transport scattering rate that's got a linear in frequency behavior at high frequencies. And to solve the problem at higher temperature, you also get T-linear DC resistivity. So all of this is just self-consistent one loop calculation that can be shown to come from some large NSYK-like construction, but that's not the real world where we don't have any large N. So that's why we do numerics. So what I have the main focus of this talk, everything is in this long paper here. Not all of the paper we cover in the talk, that's pretty long. But the model that takes on this two-band sign problem-free type instructions, which were invented more than a decade ago. There you have like two bands of fermions that are mutually coupled via some bosonic field through a Yukawa coupling. But what it does is it modifies that Yukawa coupling to be random in space. So you have a G prime of R instead of that's different on each side rather than a constant G. And like this boson is representing some magnetic order. So it's in particular, it's an antiferromagnetic order parameter. And so this model has no sign problem, which means if you integrate for any fixed configuration of the boson field, if you integrate out the fermions, you get a positive determinant. So whatever you have is under the integral over phi is a legitimate positive definite probability distribution, which you can sample. The old school way of doing this in the condensed matter community, which was actually the way Jarez-Berg et al. Did it more than a decade ago, was to use determinant of quantum Monte Carlo, which involves computing the determinant directly, or at least some number of field configurations, and then applying low rank updates. And this scales very badly. You can't go to more than like 12 by 12 or 14 by 14 system sizes, because it requires you to store a large dense matrix in order to apply the low rank updates. That's expensive in terms of memory and bandwidth. So what we've used is a different method called hybrid Monte Carlo, which came from the lattice QCD community. It's heavily used there. It's also very old, in which the determinant is rewritten in terms of a new set of scalar variables called pseudo-fermions, bar phi and bar phi star. And then now you just sample over the joint distribution of phi and bar phi. And now instead of having the determinant, you have to compute the inverse of this matrix times a vector bar phi, which is a solution of the linear problem. And one can do that with preconditioned linear solvers, conjugate gradient method. And it requires much less, it requires much less memory and memory bandwidth, because you can construct matrix-free representations of A, for instance. And that means you can also execute it on GPUs for good speed up. And this allows you to access much larger system sizes, which is good if you're dealing with disordered systems, because you want your system sizes to be large enough so you don't have to average over a very large number of disordered realizations. Another thing that this method does is it has a separate update scheme for the phi field, which relies on a flow through parameter space that's driven by fictitious Hamiltonian dynamics. And there are ways of optimizing that so that it's a good sampler. And then those are discussed in some of these papers here, and which are applied in our code. So that's the method. Now let's see what physics comes out of applying the method to the problem. So in the large N language, this model with a random Yukawa coupling, which large N means that we just solve self-consistent the Ashburn theory. What you get then is a critical point, and there's a critical fan in which you have P-linear resistivity, and on one side of the critical point, you have a gapped boson and a Fermi liquid. And the other side, the boson forms quasi-long-range order in 2 dimensions, and then you get a residual resistivity out of that in addition to P-linear resistivity. That's in these papers. Now, what happens when you have no large N and now sign-free Monte Carlo as a phase diagram definitely changes. There's no critical point anymore. You get a gapless or like a phase where the extrapolated zero temperature gap of the boson does go to 0, but there's no long range order, even a short range order in there. And then you have a Fermi liquid on one side, and then in between the Fermi liquid and like this other phase where you start seeing a residual resistivity, you have a strange metal phase with T-linear resistivity. And that now is not tied to a quantum critical point, and it actually occurs over some extended range of the tuning parameter. So between these two values of the average mass parameter of the boson, lambda S and lambda G, you get this T-linear resistivity, and there's really no long range order except asymptotically at lambda equals minus infinity. There's no quantum critical point. So this extended region of T-linear resistivity is also seen in some experiments on like highly disordered cuprate materials like LSCO. There's this extended, this is where the pseudo gap ends around 0.9, and then beyond that you have like extended region of doping in which the resistivity exponent n is close to 1. So why do we see different physics at finite n rather than large n? And the key to that is that the boson sector becomes strongly disordered at low energies. So like at this lowest Matsubara frequency, there is a significant off-diagonal in momentum component of the boson Green's function. As can be seen here, and at high Matsubara frequencies, it reverts back to being diagonal. And now if we look at, again, the 0 Matsubara frequency boson propagator and like diagonalize it, some matrix, and find the density of states of the eigenvalues, then you get this structure where, of course, it's gapped out in the Fermi liquid phase. Now in the strange metal regime, you have a finite density of states, low energies, which is approximately a constant. And then as you go to smaller values of mass parameter, there is a pileup of low energy setup. So there's, the strange metal phase is a gapless, constant low energy density of states. That's similar to actually what the quantum critical point in the mean field large N theory was with a quadratic dispersion in 2D. But these low energy modes are not plane waves like in the large N theory. They are very different, and because they're in fact localized. And because of that, there is no long correlation length of low energy boson excitations. That's not a quantum critical point. If you compute the correlation length, it's the order for coupled lattice spacings or so. So this is what the eigenvectors look like. So at low energies, strange metal, the bosonic eigenmodes look like this. They're localized peaks. High energies, you go back to something that's some extended superposition of plane waves. And you can compute the localization length using the participation ratio. You can see how the localization length varies with the eigenvalue. And then, yeah, when you go much smaller values of the mass parameter, these localized peaks start spreading out, and the localization then starts to slowly increase, and eventually it will go all the way back up to being extensive, but that's a gradual crossover. There's no sharp phase transition to like a delocalized phase. And okay, so then you have these strong disorder in the boson sector and like formation of localized boson modes, but there's no analogous phenomenon in the fermion sector. So the fermion sector in the strange metal phase, you have a sharp Fermi surface, and then the real space occupation of fermions is very nearly uniform. It's barely like a 1% variation. So we don't really see any strong disorder in the fermion sector. And okay, so yeah, but now we get to transport properties. Of course, you're restricted to computing conductivity on the imaginary axis from the Coulomb formula. We can always rewrite your imaginary axis conductivity in this form. It's a non-interacting Drude. And then you get this parameter here, which is like some scattering rate, and the data is good enough, you can extrapolate it to zero frequency and get the DC scattering rate. So you can write any conductivity in this form, but if you have a metallic system, then you're going to get some gamma, which looks sensible. It's like an increasing function of frequency and doesn't do anything funny as with small frequencies. And that's indeed what we find. When we find this something like this, it just increases with frequency. Weird, like what you'd expect for a metal. You can actually fit it to what you'd expect for a marginal Fermi liquid, the imaginary axis, with this extra correction, which is also a marginal Fermi liquid type correction, where it's a log square, it's of a log. And that extra correction is basically mostly needed only for like small values of lambda outside the strange metal phase. Like, so yeah, within years, that extra correction is small, and it's mostly just a traditional marginal Fermi liquid form that works very well to fit it. And then we can also extrapolate the scattering rate to zero frequency used by fitting polynomial spline. We don't do sophisticated analytic continuation to get the scattering rate of for finite real frequencies. We're only interested in the zero frequency extrapolation, and for that the spline works well enough. So what we find then in this region is you get T-linear resistivity down to whatever low temperature we can measure. And the slope changes as you use the value of lambda. And then, but the intercept is pretty small if you extrapolate it back. So the residual resistivity ratio is large. But it's again a sign of being fermion sector. And of course, if you go to larger values of lambda, it starts becoming curved upward. It's no longer linear T. And if you go to smaller values, then you get a negative curvature, which is an extra log correction. And then you also get a finite extrapolated residual scattering rate. See over here. So now then most interesting part is that you can repeat this calculation for various values of the random coupling G prime. And it turns out that if you take this strange metal region, the phase diagram looks pretty much the same for different values of the coupling. It's just that the numerical values of these lambda points change. But if you look at it within this strange metal region and you rescale your mass parameter, subtracting lambda s and dividing by the coupling in terms of this rescaled, I can call it dimensionless mass parameter, and then it turns out for the same value of tilde lambda, you get exactly the same transient scattering rate, even though the couplings may be different. The reason for this, which we figured out, is that the boson propagator scales as 1 over the coupling square. And even this is our bosons have dynamics that are entirely generated by interacting with the fermions. So there's no bare boson dynamics and there's no bare boson self-interaction. So everything that the bosons have comes from coupling with the fermions. So it all has to be controlled all by just this one parameter. And therefore you get this scaling 1 over coupling square for the boson propagator when you fix tilde lambda, and that's shown here by coupling square. Look at different values of the coupling, it's approximately the same. But once you have that property, then if you compute any fermion correlation function, then this coupling just cancel out, because for every factor of the boson propagator, you have factors with coupling. So it's 1 over G prime squared, G prime squared. And that seems to be the reason why, like, fermion correlation functions are universal, and you get this universal scattering rate that doesn't depend on the coupling. And this universal scattering rate is order kBt over h bar. In this particular model, the largest one we get is about 0.4 kBt over h bar. This is interesting because in many different cuprates that are chemically different and have different amounts of disorder and different amounts of bare interaction strengths probably. And experimentally look at the transport scattering rate, it's also approximately a constant value times kBt over h bar for different materials. It's constant is like what are one in experiments. So it's universal alpha constant. That's what we also find in the model. And that this definitely is something that we don't have a theoretical explanation for. It's far beyond like these large N mean field constructions that we are working with. It's definitely a new non-perturbative phenomenon. So conclusions. So if we solve like metals with random Yukawa couplings to bosonic order parameters in 2D, there's strong disorder in the boson sector, and we get a robust strange metal phase. There's no quantum critical point. We have T-linear resistivity over an extended range of the average boson mass. And even though this boson sector has strong disorder, the fermion sector is relatively clean. It has a large mean free path in a clear Fermi surface, which is also what experiments in strange metals see. So experiments should, instead of looking at disorder in terms of single fermion properties like mean free path, they should look for disorder in like a 2 fermion magnetic channel, for instance, which would be one possible bosonic sector, and try to detect like the localized overdamp bosonic modes, like localized magnetic moments, for instance. I could try to do that, find that experimentally. And another thing we find is we get this universal Planckian G-linear scattering rate, which is independent of like the strength of interactions and disorder in the system. That's it. Thanks.
What's next now that this is solved?
Correlated disorder now. So,
Oh, I see. And you think it changes something substantial to the problem?
Yeah, I mean, with correlated disorder, your interaction becomes momentum dependent. Right? So now you no longer have like a momentum independent self energy on the Fermi surface. So that's one possibility is why you can get some pseudo gap of that in addition to strange metal.
That's it. And well, Victor, so
Maybe I have a generic question. So what's the motivation for studying this model? So are you trying to explain materials, or it's just like abstract model for the sake of hooking up a model that gives you linear NT? Like why you do it? So is it explaining hook rate? So what?
Yeah, we're trying to see, what kind of, like if there are disordered interactions in the hook rates, like what kind of predictions we can get that can be tested in experiment. Like for instance, these localized bosonic modes would be like localized magnetic fluctuations.
Yeah, but if I were to think about just genetic materials, I would say that copper is probably more disordered. In wide hook rates. I don't do that, like aluminum. It's pretty crappy material.
No, I don't agree with that, right? You can form a single crystal of copper or aluminum, which has only one type of atom, and that's not going to be very disordered at all. Whereas a cuprate is doped, at least at the interesting values of doping that gives strange metals, and these dopants are not arranged in any kind of ordered manner within the samples. There's definitely more disorder.
Yeah, but there's D-wave superconductivity. By definition, it would have been suppressed zero actually. TC tau or delta tau was small without being scattering, like not scattering down. So at least in this sense, must be kind of good enough to sustain one aspect super. So I don't know if that's the
So that is definitely true, and I think that's not at odds with things I'm finding, because well, the fermion sector does end up being pretty clean. Right. So now this model had only one type of interaction, but there can be, now you have a pretty clean fermion sector, you can add another type of interaction and you can get superconductivity, which will not be hurt by this particular type of interaction that I have. So I think the disorder appears in the language of cuprates, disorder will appear in like the antiferromagnetism, for instance, but won't affect superconductivity.
Well, let's think how we should try again. So our next speaker is 101.2. Yeah, well, that's the easiest thing. And then you just share your screen. Please, you change, take it away.
Okay, so yeah, so today I will introduce this talk will basically on a quantum Zeno effect when we have a noisy integrable circuits and impurities. Okay, so this work is done with Pradeep and Jed and Matan and Ri. Should I? Oh. And basically, this talk is based on this work. You can check that out if you want. So let me start with some motivation why we are interested in these noisy systems. I think this is exactly the sentence Miles was mentioning. Feynman said, blah, blah, blah. We need quantum computers really to simulate quantum systems. So anyway, this is a good dream, but nowadays we don't have that perfect quantum machines. So what we really have is these so-called NISQ platforms where we are limited by the number of qubits and the qubits are noisy. Anyway, they are not perfect. So it is very important to understand the noisy effect in quantum computers. In a sense, we need to know what we are really running on the quantum computer, right? And here I will show you a way where we can have track analytically and numerically to understand, at least for a simple system when it's evolving under noise. So let me introduce briefly what will be covered in this talk. So we understand when there is no noise. Let's say this is some qubit chain with an impurity at the boundary. So without noise, when the boundary coupling is small, we can write down some effective field theory, which can be mapped to some Kondo problem. And when the coupling is big, of course, you can say, okay, the bulk is now you can regard it as a perturbation. So the physics will capture by some bond mode localized at the boundary. And also, we know that if we don't have impurity, we only have a noisy environment coupled with some qubit system. This system will undergoes whatever its transport property from relativistic, APZ, or diffusive, where it's noiseless directly to diffusive transport when you couple the system to a noisy environment, basically. So in this talk, we will cover that. I will show you why the environment will lead to a diffusive transport, and thus leading to two different behavior in the impurity. Where there's a bond mode, it will decay, and when it has some Kondo physics, we will undergo a quantum Zeno effect. Okay, so let me start to construct the circuit for you. Okay, so this is something in principle, you will run if you want on a quantum computer. So usually we construct these local quantum gates, apply on the qubit. So this is the qubit. So this black white is showing it's from some like kind of Neo's initial state. Doesn't really matter. Okay, it matters. Sorry, it matters. But this is the initial state. So this brick wall structure tells you the gate you are applying on this circuit. So each layer will represent a kind of a time step. This will represent a unitary matrix describing the time dynamics. Okay, so in general, we can put anything in this small box. You can apply any gates you want. But to make the things attractable, we want to use these R matrices and K matrices such that it satisfies the Yang-Baxter equation and this boundary reflection equation, so that we have more analytical tools to solve it. Okay, this is I want to go into this detail why it's integrable and why we can solve it. Anyway, we just choose some special matrices where we can solve it. And if we relate these parameters in the matrices in this specific way, we will unveil a kind of shorterized limit for some XXZ model. Okay, so let me show you when there's no noise, what is happening in this kind of impurity spin model. So if, as I said before, if we choose the parameters spatially and take some shorterized limit, we will undergo the circuit I showed you will simulate the Hamiltonian dynamics of this hand. And if we choose the parameter specifically as this model is integrable, which means we can solve for basically for the spectrons and for the energies. Okay. And so in this talk, we will only interested in the isotropic case when it has 0, and in the free fermion case when it has pi/2. When I say free fermion, I mean this model can be mapped to some free fermionic model by a Jordan-Wigner transformation. So I want to convince you that if you look at the isotropic point, this field theory will describe the low energy fields of this Hamiltonian. So if you carry out the RG, you will see, okay, it has the same RG flow as the RG flow in the Kondo problem, and they flow really to the same fixed point as a Kondo boundary CFT. And also you will see if you take the free fermion limit, it will flow to the same fixed point, but with some like different starting point. So the reason why I introduce also the XX point is we will see later. And since it can be mapped to some free fermionic model, it is easy to solve when we add noisy on. Okay, so so here are some properties of the impurity model when we don't have noise. So basically, we will only focus in this antiferromagnetic region because here, in a sense, it's kind of flows to some trivial fixed point, and the impurity is on screen. Anyway, we will just focus on when the coupling is antiferromagnet. So when the coupling is small, we will have a Kondo physics basically. So this is evidence why it's Kondo. You can see here when the coupling is small, at least the relative density of states is Lorentzian, and the width of it captures some Kondo temperature for this problem. And if we look at the local magnetization at the impurity, as we increase the magnetic field, the global magnetic field, we will see this magnetization grow kind of slowly and smoothly until it's fully polarized. And here B is some parameter we used in the calculation. It can be mapped one-to-one to the boundary coupling as a simple relation like this. Okay, so when the coupling is big, we will have a boundary bound mode close to the impurity. So again, if we apply a magnetic field in the bulk, the magnetization at the impurity will experience some discontinuity. And this discontinuity is exactly because there is a massive boundary bound mode in this model. Okay, and this is for the isotropic case. And for the free fermion case, again, it corresponds to the specific eta. And since you can see from here, this is just XY coupling, you can do some Jordan-Wigner transformation, map it to a free fermion model. I think this is correct, up to some trivial numbers. Okay. And again, we will have the same kind of phase diagram where we will have Kondo phase and bound mode phase. And if we look at okay, this is another signature. If instead of looking at the magnetization, we look at susceptibility. We will have a finite susceptibility at 0 temperature, and this is a signature as a Kondo model since the impurity is kind of screened by the bulk. And also at higher temperature, it's again experience some Curie susceptibility as 1/T. So this indicates the kind of asymptotically freedom for the Kondo physics. Okay. Anyway, these are just evidence convincing you these two models really shows the Kondo physics. And here at high temperature, it's again free, but at low temperature, it has negative susceptibility as a result of the impurity forms a kind of singlet with a boundary. Okay, now knowing without noise, this model has some Kondo physics and some bound mode physics, we can ask the question, what happens if this system is explored to some noisy environment? So the way we model the environment
at least the Markov environment is by modeling the unitary dynamics with an extra Lindblad term. So here the unitary evolution part is the usual Hamiltonian evolution with this Hamiltonian I introduced you already. Okay, and the Lindbladian part here, we introduce a gamma as the dephasing rate, kind of describing how strong our system is coupled to the environment. And also these L's, these Lindblad are called Lindbladian jump operators. Here we will choose them to be sigma z for the sake of integrability. It's kind of describing the dephasing error when we really put this quantum circuit on a quantum computer. It's not a bad approximation, I would say, because there are some quantum computers are kind of dephasing error dominates, and there's other, for example, bit flipping errors are less than this dephasing error. Anyway, it's simply a certain kind of error. And it is worth to mention that this Lindbladian is integrable only at this 3 fermion point. And I will explain why is that. So the way to show this Lindbladian is integrable is by reformulating this Lindbladian equation in a different space. And this was introduced by Prosen, I think. We can double the Hilbert space into a so-called Liouvelian Fock space. Basically, we just write every matrix into a new state. So the reason why we do that is we want to map the density operator, which is a matrix in the Hilbert space, to a vector in this new space. Therefore, the Liouvelian evolution can be mapped to a Hamiltonian evolution in this new space. So we know how to do a Hamiltonian dynamics. So by doing this mapping, it is easier for us to solve this problem. But it is worth to mention that after this mapping, since the Liouvelian itself is non-unitary in the new space, the Liouvelian, I think this is especially at the 3 fermion point, can be mapped to this non-Hermitian Hubble model. So here the kind of the noise comes in this to imaginary part in the effective Hamiltonian with some transformation. Okay, I will not go to the detail of this transformation, but one thing important to mention is that although this Liouvelian looks like interacting, the correlation function in the original space is still closed within themselves. This is a result since both the original Hamiltonian and the Liouvelian jump operators are quadratic. So this kind of free Hamiltonian property are also valid even when we write everything in the Liouvelian space. And also the corresponding dynamics of this endpoint correlation function will be the same if we look at the dynamics of the 2M particle sector, for example, to the new effective Hamiltonian. Okay, these are just some mathematical facts. So then we can ask if we really want to solve for the 2-point correlation function, then we just need to diagonalize a effective Hamiltonian, which is like a 2-particle quantum mechanics Hamiltonian with some imaginary, at least non-Hermitian Hamiltonian. And the reason why we want to look at 2-point correlation function is simple, because the mechanization, which is the most important thing when we look at some spin system or Kuiper system, can be expressed in terms of the 2-point correlation function. This is just a simple time dynamics when we do any quantum mechanical problem. This is overlap, this is eigenvalue, or this is kind of the expectation value at each eigenstate, and this is time evolution. Okay, so this just allows us to calculate the mechanization as a function of time when we check the volts. And also it was to mention that alpha here is the overlap between the initial state and the eigenstate. So we write down the equation, then we need to ask how do we solve it. Since I mentioned to you this Liouvelian itself is integrable,
we can write down the wave function, which takes a beta ansatz form again, and this is its eigenvalue. So the way we solve it is we write down the boundary conditions and the scattering matrix for this problem, and basically the K and Q are quasi-momentas, which are solutions of the beta ansatz equation, which are these two algebraic but transcendental equations. So after we write down the equation, we stare at it for several minutes. And we will know the solution of this these two equations. So basically, and the solution of it forms into four different classes. So one of it, when both boundary scattering matrix and bulk scattering matrix are regular, we have this kind of trivial band where the K and Q quasi-momentas are the same as the one when we have basically free electrons. And also another solution is when only the boundary matrix is singular. So we will have one particle being free moving and one particle forming bound state at the boundary. So this is another kind of solution. And also the most interesting solution here is so-called diffusive band. And this kind of solution are like two quasi-particles are kind of forming a bound state due to that imaginary coupling and result into a purely imaginary energy, which means everything in this mode only decays. They don't have any oscillation dynamics. And it goes like a free quadratic Hamiltonian, but it's purely imaginary. Okay, and the last two solutions, which are not always existing, we call it double bond mode, when both the boundary S matrix and the bulk S matrix is singular. So we can ask when does these two special solutions occur or not, and exactly the boundary of this double bond mode solution exists will distinguish the Kondo region and the bond mode region when our system is explode into noise. And the reason is following. So here the alpha, as I maybe mentioned before, the alpha are the overlap between the eigenstates and the initial state. And in this specific case, it's taken from the overlap from the eigenstate and the Néel state, which we choose to be our initial state. So the state with bigger overlap will dominate the early time dynamics, of course, since they have a bigger overlap, right? So we can see here, when there is a bound mode, a double bound mode here, these two states dominates and have a non-zero real part, which means they will oscillate as time evolves, and only these two states are dominating, right? You can see all the other states have very small overlaps, which will not oscillate. So anyway, the existence of this double bond mode indicates whether we call it a bond mode region when these two states exists. And also for the long time dynamics, since everything just decays with their corresponding imaginary part of energy, the only surviving solutions will be those with the smallest imaginary part, which are these states in the diffusive band. And the reason why we call it diffusive is because this band scales as an energy inverse, and also as I mentioned before, it scales like, so if you think energy is inverse time, so you have energy scales as imaginary k squared, so you have something like time scale as minus time scale as some like space squared. This exactly will be the diffusion equation. I will show you this in a detail later. Okay, so with this knowledge from the spectrum, which are the equilibrium property of the system, we can directly look at the dynamics of this system. So if we prepare the system from a Néel state, and just evolve it. You can see when J is big, which are these dashed lines, we have a bond mode oscillates when there's no impurity, when there's no noise. And as we increase noise, this bond mode starts to decay and oscillates weaker and weaker. However, for small boundary coupling J, where we are in the Kondo region, if you remember, the Kondo impurity will decay fast when there's no noise. But as we increase the noise, the Kondo impurity will decay slower and slower. This is what is called Kondo-Zeno effect. And the reason of that, we will argue that since when gamma is big, since when gamma is as gamma increases, the noise tries to heat up the bulk, and thus, since the Kondo problem has a asymptotically freed nature, so this spin will decouples with the bulk, just not evolving at all. And also, it's worth to mention that if we look at this long time limit, this is time here. So if you look at really long time dynamics, the time dependence is independent of the boundary coupling. It's only dominating by the bulk property. And again, this is because of the Liouville gap of the bulk, which is independent of the boundary coupling. Okay, so this is for the free fermion point. And we can ask the same dynamics of when we look at the isotropic point when the system can never be mapped to any free fermion model. But the physics is the same. We also see a oscillation decay in the bond mode region and the Zeno effect in the Kondo region. And also the long time behavior is independent of the boundary coupling. So in principle, these two models are quite different when there's no noise, but since after we add the noise to the system, they behave similarly. So we should ask the reason why they behave so similar when we have noise. And the reason is that when we have noise, the bulk just becomes diffusive. And since I argued before, if you just Fourier transform this thing, you will have energy minus, or maybe I energy plus k squared, something like that. So energy will scale as k squared here. And this exactly gives you the diffusion equation. And so to see this bulk is really diffusive, we prepare here in a different initial state from a domain wall kind of state where everything is aligned up from the left and aligned down from the right. And if we evolve the system, the solution for the diffusion equation will be some arrow function. And here the dots are the numerical dots we simulated when we really do the time evolution of the spin chains. So since they really every single data collapse on this solution of the diffusion equation, this indicates our bulk is really diffusive. So, and since our bulk is diffusive, and the diffusion constant, I forgot to mention that the diffusion constant is increasing as we increase the noisy coupling. So since the bulk is more diffusive when we increase the noise, the spin at the impurity is harder and harder to propagate into the bulk when it's diffusive. So, and this thing results into, again, the quantum Zeno effect. Okay, so it's the end of talk. Here are the conclusions. So when we have dephasing noise, it will affect the impurity differently when we have a Kondo physics or a bond mode physics. So in the Kondo region, increasing dephasing rate will slow the impurity mechanization decay and lead into a quantum Zeno effect. But in the bond mode region, so initially its dynamics is governing by this double bond mode, so the bond mode will decay faster, but eventually also exhibits a quantum Zeno effect since this bond mode just decays out and all the rest of the part is kind of have some Kondo physics. So, and also the reason why we have a quantum Zeno effect is due to the bulk being diffusive. because of the existence of the noise, and increasing the noise does not allow the impurity to communicate with the bulk, since it's diffusive. Okay, I think that's the end of my talk.
I guess it makes sense that everything becomes diffusive, but this is on the level of the average. So if you would do some like full counting statistics or look at some more refined quantity, do you still expect that everything is the same in free fermion and XXZ?
I would think they are the same if we look at the Lindblad, right? Because Lindblad, in a sense, is you already average over all the quantum trajectories. But if you really ask what happens for each different quantum trajectory, so probably things are different. Especially at least the entanglement, for example, will not be averaged over these dimensions.
Yeah, that makes sense. Well, even time, I think, which is. Yeah. The last speaker of the day is Victor Kalitsky, who will speak about machine learning and many-body physics or something. Oh. What did I do?
It's incorrect title.
Oh, you changed it. So
I didn't. You changed.
Oh, I changed it. Wait. I thought I saw that.
Anyways, what is that I'm supposed to do?
Oh, I saw neural net. I think the easiest is to log in on Zoom.
Oh, like,
and then project on Zoom.
Like
but you send an email. Yeah, so you should search. But in today's email, there's a link to Zoom.
This one.
Yeah, exactly. Then that's perfect.
So I don't turn on the microphone, right?
No, because then we'll get some feedback if this is supposed to pick up your yes. So the real title is.
Yeah, so I'll talk about that. Thanks very much, Chris and Vadim, who's not here, for inviting me, and thanks for staying until the end. So indeed, it's a pretty esoteric talk, and kind of a warning. It's a compression of a 1 hour presentation, kind of reviewing our work, primarily with Brian Swingle and Yongxiao Liao, who was my postdoc. Now she's a professor at the Royal Institute of Technology in Stockholm. So kind of this review kind of revolves around the notion of glasses. So kind of a high level kind of BS level of introduction is that I'm working under the premise that 3 different class of systems or platforms, such as just old-fashioned, physical Hamiltonians, quantum circuits, and indeed, as you mentioned, neural networks, so connected in some way through statistical mechanics, and kind of the premise here that any phase or regime that is possible in one class of system is potentially realizable in another. And I'll be particularly interested in glasses. So the outline of my talk is this. So first I will kind of, given time, give a quick overview of our recent work on glasses, spin glasses. So in particular, I'll emphasize Thoudis, Anderson, Palmer approach to equations, which are kind of Ginzburg-Landau for glasses. Then I'll talk about some understanding of quantum spin glasses, which I actually personally find more intuitive than classical. And I'll talk about some ideas on how to realize this class of model potentially on quantum circuits. And then indeed, sort of the esoteric part that Chris was referring to is that then we'll talk about relevance between well, actually commercial neural networks and spin glasses. In particular, we're going to follow neural networks through the training process, and we'll see that kind of the big question here is why do these things work actually? So from physics perspective, and my answer will be you start with a random collection of couplings, they call weights, and then training the network means breaking the glass, choosing an order which kind of reflects, let's say, classification problem that you are solving, and strengthening it, which increases the accuracy. So this is sort of the ambitious plan of what I want to talk about, which may or may not pan out. So I'll start with highlighting this paper. So I'll just assume that you know the canonical model of a spin glass, which is Cherenkov-Kirkpatrick model. Let's say in this case, we're dealing with using spins with everybody interacting with everybody with random coupling, let's say Gaussian distributed random coupling. And of course, you know, there is very well-known solution to this problem based on replica symmetry breaking. But there is another approach to it, solving this model exactly, which was actually done by, well, Taulis, Anderson, and Palmer back in '77, where they put together a mean field approach to the same problem. So, and for my purposes, that hopefully will become clear later. So this mean field approach is friendlier than the replica approach. So the top equations, Taulis, Anderson, Palmer equations or approach is sort of a generalization of Ginzburg-Landau to glasses. So in Ginzburg-Landau, of course, what we're doing, we're kind of Taylor expanding free energy near a minima. Could be just one minimum at high temperatures, just zero, or let's say two minima, you know, up or down in the low temperature phase. So in the case of glasses, you will have to expand kind of around many different minima potentially. And so the way kind of technically to derive it, it's actually not that complicated. You can read the paper, it is pretty readable, is that you introduce the free energy and essentially Lagrange multipliers that enforce basically this mean field. So SI could be either plus or minus one, something sitting on the side, and this is sort of average unitization, which is not a discrete variable, it's a continuous variable, and that's that. And then am I a given? No, it's not given, it's for you to find. That's our goal, to find this MI, if any. So the type equation essentially is just this constraint which satisfies basically everything has to be self-consistent. And what has been proven to some degree by Taulis, Anderson, and Palmer is that you can get actually exact partition function of the say Cherenkov-Kirkpatrick model by just summing over solutions to these tap equations. So the equations, look like this. And at high temperatures, you just don't have any solutions. And at low temperatures, you have a massive number of solutions. So that's not that simple. So, but what's interesting is that, so you're kind of summing over all these solutions, low temperatures. Now, the equations that you get, as a result of this exercise, involve sort of more or less familiar mean field part and so-called Onsager term, which is nonlinear right here. And well, that's the tap equations that actually are very practical. In fact, they're much more, user-friendly than the replica approach. And for example, if you're interested in transition temperature into a glass, what you do, you're saying, well, M's are small, so let's linearize these equations. So you will just have a system of linear algebraic equations, and you set determinant to 0, and it will give you a TC for spin glass, which is exactly the same as you would get using replica symmetry breaking, let's say. Now, again, I'm just reviewing something very quickly. So let's just establish that there is such a thing as tap equations. What we've been looking into, and this is sort of first part of my talk, is various kinds of quantum glasses. Now, well, there are different models which kind of fall into this category. The one we used is so-called phi-spherical model. So this is actually a classical version of this model. The model is, well, sort of similar to Cherenkov-Kirkpatrick, except, the couplings can be not between just two pairs of spins, but between like a cluster of p spins. And this thing, the coupling is a random variable. So it's a little bit like SYKH, but in this case, it's classical. So one way to quantize this thing is to essentially promote the sigma into a coordinate quantum conjugate to some momentum, sort of. with canonical commutation relations, in which case this thing becomes a random potential and this becomes a kinetic energy. And by tuning sort of the mass, mu, you can control the quantumness of the model. And then you have energy or temperature variable that you already had in the classical problem. So it turns out that, and it's primarily based on the work by Letitia, last name is not easy for me to pronounce, by Letitia, I'll just say by Letitia. So who derived actually quantum generalization of the TAP equations. So just like classical Thouless-Anderson-Palmer equations are sort of classical Ginzburg-Landau, you can view quantum TAP equations as time-dependent Ginzburg-Landau. So you're attaching a time variable basically to a quantum fluctuating field, and you're writing it as a path integral and all this stuff. And just like that, so you can also derive self-consistency equations, and actually it becomes sort of exactly soluble model of a quantum spin glass, and you can do, well, all kinds of things. In particular, you can define complexity, which is roughly the number of states, solutions basically to TAP equations, for given energy. So that's one way to think about it. So anyways, I'm not going to dwell on this too much, except that this thing exists and you can read about it in our papers. I'll just mention that we studied this model and sort of looked into its phase diagram. And so it has a very interesting, in my opinion, intuition. So first of all, I mean, what do we have? So we have, like, if you turn off quantumness, if you kill the quantum stuff, so you just have a classical model, but otherwise you have two parameters. One is basically temperature energy, the other is quantum fluctuations, and you have actually more than two, but roughly sort of ergodic and non-ergodic regions. And there's a transition between the two. And what we did is we looked into this model from the point of view of quantum chaos. So in quantum chaos, a figure of merit oftentimes is a spectral form factor. So roughly, well, the definition of the spectral form factor is simply the average of, trace of the square of the trace of the evolution operator. The meaning of it is kind of Fourier transform of, two-level correlation functions. And it has a canonical form if you are in the chaotic system. It has a certain behavior. So if you're, have been working on this, you probably know what it is. It involves sort of a deep ramp and a plateau. And so what we found is that so we basically looked at this quantity.
T small here is T large there.
No. Oh yeah, here, yeah. So basically there is so essentially, so random matrix theory means Wigner-Dyson sort of level statistics. So you can look at the distribution function of eigenvalues of a random matrix, or you can play games with Fourier transforms of correlation functions. One of those involves spectral form factor, and it has this so-called linear ramp, which basically is a hallmark of quantum chaos. So Michael Berry has worked quite a bit on that. So it has to do with interference of trajectories where you can start with a different point. So this linear ramp is really, you can get around it. So for any chaotic system, you have this linear ramp, and this is sort of when we are usually dealing with quantum chaos, that's what we're looking for. And what we were interested in is, what is the difference basically? Okay, we have integrable systems, they show Poisson statistics. We have quantum chaotic systems, they show Wigner-Dyson statistics. Is there anything else? Well, there is something else called glasses, and we're just interested, what is the level statistics of glasses? That's the question that we're interested in. But the proxy for this was not actually the level statistics, but the Fourier transform of some correlation function is called spectral form factor. So I'm not going to explain it because it would have been a different talk. But the point I'm trying to make is that we found that this this ramp is scaled by the exponential of complexity, and it's very, very easy to connect it to the following picture. That's why I said that quantum was actually simpler in my intuition than classical. So random matrix is a random matrix. You just have a bunch of stuff and diagonals, all random matrix elements. So if you want to visualize quantum glass, basically it's a block diagonal matrix where each block is Wigner-Dyson, but different blocks don't talk to each other. And there's some hierarchy of these blocks.
There are different sizes?
Yeah, in principle, there are different sizes. In fact, replica symmetry breaking kind of, if you need it, in this case, you don't even need it, sort of determines the statistics of the sizes and distributions of this and that, but that's not even the point. So the point is that you have different blocks which thermalize very quickly, and there's kind of zero measure set maybe of diagonals which couple them a little bit, but basically that's what it looks like, and I think it's easy enough to imagine, right? So like Poisson matrix is diagonal matrix, that's the integrable system. So random matrix is random matrix, you just have dense matrix with all random matrix elements, and glasses is this thing. So that's basically a take-home message. If you didn't say anything else I said, so this is maybe the only thing I want to take home from this conversation for now. Now, and one of the things we've been working on, again, being mindful of the time, I'm just giving kind of elevator pitch of this, is that it would be kind of interesting to realize something that I call a glass in the quantum circuit. Why? Okay. So as I said, possibly we can state that pretty much any phenomenon that we can have in a Hamiltonian system, you can also realize in a unitary dynamics, right? Integrability, certainly ergodicity, localization, logical phenomena, it's all been done. It's been gamed for a long time. Now, most in integrability usually requires a lot of fine tuning. You go one step to the left, one step to the right, you break it, and you fall into basically random matrix, which is not that interesting. Eventually you lose information. So there's not much fun in that. So, and then you can ask a question, is there anything else? So, and then, well, yeah, there is something else, and it's called glasses. So let's see if we can realize something that you can call a glass, but not in a Hamiltonian system, but in a unitary evolution. So before doing so, I want to have introduce a model. Actually, Boris here and Kravtsov and their colleagues have been working quite a bit on that. So this is not a glass, but it's a kind of stepping stone to something I would want to call a glass. So the model is designed to show a transition between an integrable system and the chaotic system. The model is not particularly physical, it's just a mathematical model with which you can play pretty well. And so the model is kind of simple. So it contains, it's a Hamiltonian, it's a matrix, n by n matrix, which has two parts. So one part is just diagonal matrix with Poisson statistics, that's my quote unquote integrable part, trivial enough. And then you add a random matrix, let's say unitary ensemble, although it does matter. So basically, some sort of a matrix. So if you turn it off, clearly you have an integrable system with Poisson statistics by construction. If you make this guy very large, well, it will dominate whether or not you have a Poisson part, doesn't matter because everything will be dominated by the chaotic part. So you have a transition therefore from Poisson to Wigner-Dyson, and it's actually an interesting transition with a lot of details. So the model is deceptively simple to write, but actually it's very rich, as you can see from Kravtsov's papers in particular. So the parameter here is actually not lambda, but this gamma, which is n is the kind of matrix size. So if gamma is large, so you basically kill the chaotic part, and the only thing that's left is Poisson. It's an integrable regime, gamma equal greater than 2, right? Gamma smaller than 1 is on the contrary chaotic regime, and then there's actually an interesting intermediate phase, which I can talk about exactly. It could be another talk actually, but it's just I will just note that in the middle there is this fractal dimension sort of phase. So it's a very interesting model. But there is this model well studied called Rosenberg-Porter model, which describes transition from integrability to chaos. Now, and well, we can also look at the those who care. So I mean, you can also calculate spectral form factor. So this corresponds to chaotic regime. So this corresponds to just Poisson statistics, which means no correlations between levels. And this corresponds to this fractal regime. Now, so what I want now is to construct kind of generalized version of this Rosenberg-Porter model, which I could call a minimal model of a glass to chaos transition. And the model will look like this. Well, that's what I want to call a glass. So this, I say, well, this will be sort of a model of a glass where I have a block diagonal Hamiltonians, each of which is being thermalized very quickly. And then I add to it a conventional RP model, a fully chaotic matrix. And so this would be a generalized RP model, which will be friendly enough that I can transplant it on a unitary circuit. So that's my goal. And so if you want to know more just about this model, so there's this work by Brian Swingle and collaborators and myself, so where we studied
this model in great detail, including its spectral form factor, etc. But now, so what we also were interested in is this: can we generate something like this, but without a Hamiltonian? So in this case, I don't have the notion of a sum of two Hamiltonians. I have only the notion of products of unitary operations. And the answer is yes. So essentially, the analog of the model I had just written on the previous slide is the following. So you have a structure. Basically, what you want to add a random matrix to your unitary evolution that you can turn on and off. So in the Hamiltonian context, you can just multiply it by a constant that you can make small if you want to. And that's how you tune between being, having a random matrix and not having a random matrix. So here, what we want is sort of like a block diagonal part, which will come from here, and a random matrix part, which will come from here. And so this guy in the middle is simply a collection of single spin or single qubit gates, where the phase is drawn from an ensemble where phase could be, let's say, from 0 to sigma, where sigma is a parameter for me to choose. So if sigma is very, very small, let's say if sigma is 0, there's no phase. Of course, these guys will just collapse and it will go away. And if sigma is 2 pi or 1 or whatever, so then it will become random matrix and dominate everything. So this model turns out to be exactly soluble, actually, which is kind of nice. And what we can find is all properties of this model, including slow relaxation, and we use a sigma model to solve it. But mostly it was done by Mingxian Liao, who's now, as I said, professor at KTH. So anyway, so this was kind of, I think I probably spent most of my time on this first part, but this was a discussion of a few works that we've been doing, around glasses and quantum glasses and whatnot. And now in the last 10 minutes, Teresa, if you allow me, so I will talk about the thing that you announced, which is kind of the crazy part, but I'm really excited about it anyway, so I don't really care. So it just turned out to be really interesting. So, what I want to observe is that there is a natural correspondence between just a standard, vanilla neural network and statistical mechanical models, including actually glasses. And the observation is the following. So take, I don't know, a picture from Google, insert in your PowerPoint, which is what I did. I have no idea what's. So, and then, you have these neurons, and so we have, what are the ingredients? So the ingredients is that you feed your data at the left boundary, you read it off at the right boundary, and you change the weights between the neurons. So what do these weights do? So they, when you propagate information through this thing, so depending on the weights, neurons either fire or don't fire. So there are all kinds of so-called activation functions, but the simplest one I will take is just step function. So if this guy, so these are the weights, and this is the sum of all these weights from the previous layer, and there is so-called bias. So if you stare at it for like 5 minutes, you will convince yourself, and they just gave kind of Hopfield Nobel Prize basically for this, so that this looks like Ising spins, even though it doesn't really matter if it's step function or not. So this very much looks like spin-spin coupling, and this very much looks like a magnetic field. So for every state of a neural network, I can write a classical spin Hamiltonian and study it to death. And this is what I want to do.
So Hamiltonian will give you probabilities. What it would give you?
Well, let me just write it.
Or dynamics.
Well, whatever you want it to give, it will give it. I can just write and study and say, okay. So basically, I'm trying to carve out a space for physicists to work on this. Like, there are people who code and sell these tools. There are people who prove theorems. And I want to look at it from a physics perspective, like Feynman style physics. And for this, I need to translate it by language. That's what I'm doing. And I do so by writing a Hamiltonian. So given this network, so the Hamiltonian is simply this. So instead of calling it weights, I will call it couplings. Instead of calling it neurons, I will call it Ising spins. And training network means changing the couplings. So you have a flow of the Hamiltonians as a function of training. And the question that I'm going to ask is, what are the phases of this model? What is the transition temperature of this model? So I'm going to view it as a classical StatMech model. And then, by the way, it's very easy to quantize it in a natural way. So there are all kinds of people, working on so-called quantum neural networks, which is completely different. So here, I think it's kind of obvious what to do in some sense if you want to quantize. So anyways, and what we did, and so if I run out of time, which I think I already am, I'll just get to the point. So, so what do you do when you train a neural network? So you feed in data and you train it. And so you change your weights. So in my language, I have a family of Hamiltonians for every step of my training. Every time I train it, something changes with my Hamiltonian. So there is a variable which is called time, training time. And for every moment of time, I can look at my Hamiltonian and ask, what is its phase? And then there is temperature. And I can ask, you know, is this phase, what temperature this phase is this phase melts. And in all actually neural networks, the convention mostly that you start actually with random couplings. And this happens to be analytically, I can prove that's actually a spin glass. So you start with a spin glass, and then as you train, you destroy the spin glass, and you pick an order, which is sort of associated with whatever it is you're doing. Let's say cats are up and dogs are down or whatever. And then as you train further, your transition temperature goes up, which means your order becomes stronger and stronger, which is good for your, allegedly, so for your
What is
result.
a neural network? How we define temperature?
Well, I don't define them. I'm just saying this Hamiltonian, let me study it, like the old-fashioned way. So yeah, so first thing we did was just took this, we took this thing, the layer, the only difference between Shark and Kirkpatrick, and what we did was the layer structure of the Hamiltonian. And it turns out that this model is exactly soluble using replicas and tap equations. So this is a starting point of any actual neural network. And well, there are some subtleties related to the fact that it's a layered structure, which reflects in the structure of the couplings, which has this form, if you kind of relabel the spins. And what we can do, we can just use the old-fashioned replica tree, which is the following. So you obviously create a lot of copies of your system, and then you essentially introduce what I would call Haber-Stratonowicz fields, and ask at what point this replica symmetric solution becomes unstable. So Dries was talking about something like this earlier today. And it turns out that actually you can solve it exactly for this layer structure and find, for example, transition temperature. So you do prove that it's spin glass, you do see an instability towards replica symmetry breaking, you actually find the transition temperature. So another exercise you can do, I think I still have like 5 minutes, so is you can go back to my first slide, which is tap equations. So the problem with replicas, they're not generalizable to training. When I start training stuff, I can no longer do things with a pencil and paper. I will have to do something on a computer, unfortunately. So, and I don't know how to do it with replicas. But tap equations are easy. So you essentially, yeah, so we're going to write the free energy for this model. We're going to write the matrix. We're going to write basically the Ginzburg-Landau, quote unquote, for this model. And we're going to linearize it, which will look like this. And the moment this matrix acquires, the right eigenvalue, I have a transition into a glass. And then we can compare the two solutions. And sure enough, it's all analytical. You find that the initial state of actually any neural network is in fact a Cherenkov-Kirkpatrick spin glass with a certain transition temperature, which I can even find analytically, which is kind of nice. So the next thing we do, which is kind of the crazy part, is that we took an actual like commercial neural network with data set that people sell or something. And in this case, it was 60,000 handwritten digits, which like 0 through 9. And the job of the neural network is to find what digit you just wrote. So, and you train this network, at every point of training, you detect your couplings and you explore the phase diagram as a function of this process. That was sort of the idea. So for those of you who are actually familiar with this, so we use this sort of parameters, but let me just skip this and get to the point. So we trained it, just the usual way. So I found a pretty good validation error, which means the percentage of time you get the wrong result. And then the most interesting thing is that for every point during the training process, we would write a Hamiltonian. T here is a step of your training. So t equals 0 is completely random, t equals 1 is not random, and then eventually you approach kind of something useful. And you can easily write the type equations, and what you can find, for example, transition temperature from a high temperature phase, which is just a paramagnet, into whatever low temperature phase is. And the second part of this exercise was to figure out what the low temperature phase actually is, which is not entirely trivial. And yeah, by the way, the transition temperature, for some reason, I don't understand very well, scales pretty well as a power law with this training time. So that's very interesting. But the real interesting part is trying to figure out the nature of the phase. So there, again, given the time, I'm not going to go into the nitty gritty, but there are two kind of pieces of data that helps us figure it out. First is simply taking the matrix of spin-spin couplings, or in the neural network lingo, weights, and looking at the eigenvalues of this matrix. And at initial time before training is just basically the analog of Wigner semicircle law, because you're just dealing, well, modulo the.
So it's random matrix. It's
Well,
not glass.
Huh?
It's not glass. It's random matrix. And
Well, I mean,
But
yeah.
this is the J matrix, right? No.
Yeah. So yeah, which is a random matrix, and it is a glass. They're not mutually exclusive statements. And then this matrix, if you train and you look at the spectrum, you will see kind of this eigenvalue peeling off. And there is a little bit of an art here, because we know that it does happen when you enter the ordered state. That's one piece of data, that eigenvalues are splitting, and this is typical to an ordered state. Another kind of more sophisticated part, which will require a little bit of more thinking if we want to dwell into this, is looking into the structure of the tap equation. So tap equations also have a matrix that you want to diagonalize. And then what you're interested in is how many solutions do you have once you enter the glass. So if you enter an ordered phase, you just have like one or two solutions, up or down, and that's that. If you enter a glass, you have an avalanche of solutions. And so what's plotted here, again, without going into details, is the blue stuff is this like sea of solutions which correspond to a glass, versus this thing, which corresponds to essentially an ordered state. So, and I'm almost done. So, and sort of the picture here is the following. So what's plotted here is the temperature, transition temperature from low temperature phase into a high temperature phase, the eigenvalues, the largest eigenvalue of the J matrix, and the first relevant eigenvalue of the STAP matrix. And the picture here is that once you start slowly, with something totally useless, which has no information whatsoever, just random matrix, and slowly but surely you crack the glass. And once you crack the glass, you kind of pick the order that actually corresponds, let's say, to a classification problem. And then something interesting happens when you strengthen this order and go into high accuracy sort of this training. And this happens with so-called lazy training, which basically means that when you do gradient descent, well, you do Taylor expansion, and the steps of this Taylor expansion are small. That's what means lazy.
why you call it crack the glass and not crystallize the glass?
Well, okay, fine. I like it. That's why. So I like the word crack. So and then if you do it very quickly.
Order.
Yeah. So yeah, but this order is subtle. So it's not like an obvious order, which is like everybody up or everybody down. So, but you lose the massive number of low energy states. So that's the point. But it's not an obvious order. It's something very non-local. And well, if you do things fast, which is called rich learning, I think it's from Ronald Reagan, who said you can be either lazy or rich. So this is where it comes from. But so you immediately actually crystallize the glass, as was suggested. And anyways, so basically the bottom line is, this is my summary, essentially the interpretation that I myself am very happy with, is that, from a physicist, I want to understand why this thing actually works. So what happens is that at least for classification tasks, the initial glassy state is quickly destroyed by training. So we see it for many different tasks. So a new phase with a hidden order emerges. So, and this is evidenced by a small number of eigenvalues that can be peeled off the bulk and complexity of this Thouless-Anderson-Palmer states. And after a hidden order is detected, it's further strengthened by training, and the critical temperature increases monotonically and scales as a follow of the training time. So that's sort of the first step. And what we're working on now is trying to quantize this thing, which I'm not going to talk about. I'll just mention that the guys who've been doing actually all the work are Mike Winner, who went to Institute for Advanced Studies, my student, Princeton, and Richard Barney, who is graduating this year, and he's great, and you should hire him as a postdoc. Yeah, thank you very much. Yeah.
Initially, I thought that you're saying that there is a random matrix and there is a glass with just the pieces of random matrix arranged in some kind of a diagonal order. Now you're telling me that it's essentially the same. Or if it's not the same, that's what I'm actually starting from. I'm starting from random, or yeah, I'm starting from glass when I'm doing neural network.
So I mean, it depends what you mean by it. So so you have
What you mean?
So I mean, yeah, you have so when you write your Hamiltonian, you have Jij, whether it's neural network or Shannon-Kirkpatrick. Let's say Shannon-Kirkpatrick. So Jij is a random matrix. Do you agree with this? In Shannon-Kirkpatrick model. Well, that's what I'm referring to. So it's a convention in actually any neural net. So if you start with that, basically, you're just saying, I don't know, I don't have any information about what I'm going to do. I don't know what I'm doing. So that's my random matrix now. And if I now say that there is equivalence between this neural network and a Hamiltonian, which I'm saying is kind of obvious that there is, so you can study the phase of this model. And I'm stating that the phase of this model initially is a glass. That's the statement. Yeah.
Yes.
Yeah.
So thank you, very interesting. So I think can you say again, where is the striking signature that you observe in your model when you cross the transition and you go to the order at the phase, so you crack the glass? Because I was wondering if your neural network, say, finds a solution that is not the true one. So if it fails somehow, so if you show that sometimes the percentage, the accuracy of a neural network can be good up to a certain level, right? So I was wondering if you can exclude those false results by looking at certain property of your
Yeah, so I think what you're asking is that when it fails, so it's not a property of the how to say, so the network is still the same.
Yeah.
So you fix the ways, you're done, it's frozen, it's fossilized. So when you've trained it, you're done. Your Hamiltonian stays. Now, from the physics point of view, what you're doing, you're feeding something to the left boundary and let it propagate through this network with fixed weights, and you never change the weights anymore. Sometimes in most cases it works, in some cases it doesn't. That's the validation error. So in my approach, I don't know. I mean, I don't know what it would correspond to necessarily. So I'm studying the state of the network, not the dynamics through the network, which is the actual usage of it. So usage of it is you freeze basically fields. You apply, and if you want physical intuition, so feeding in the data just means applying magnetic fields, because like 0, 1, 0, 1, 0, 1 or plus minus 1 is up-down fields, and then letting this thing propagate through the network and reading off whatever happens at the right boundary. Just you go through one boundary through a spin system, read off something at the right boundary. So that's the picture I like as a physicist.
But then
So-
when you cross the transition, somehow something changed. Now, so you are not anymore in a glassy phase. You have, let's say, trained enough your.
Yeah, so before you basically transition, your results are kind of crap. So you train it, but the results that you get are very bad. So most of the time you just fail. And then suddenly you start very significantly, it goes kind of hand in hand. So basically you train, and your accuracy is just very bad. And then suddenly you transition from a glass, and it's just heuristic observation, the data. And your results suddenly become much better. So it's like 50%, 60%, 70%. And this corresponds basically just heuristically with this happens here when you kill the glass, and then start increasing the transition temperature. And basically this curve kind of follows the accuracy,
I see.
which is kind of interesting. But I don't know what else. It's just one paper we wrote, and that's about it.
I'm going to use my chair
Yeah.
privilege to ask the final questions, because you just mentioned exactly what I wanted to ask. So
Okay.
in this calculation, you don't put boundary fields?
What boundary?
Because you just mentioned yourself that basically actually inputting and reading out the data is basically applying a magnetic field on the left side of the problem or on the right side.
But this is okay. So there are two
So
different-
because then you can drive a transition, I think, from the boundary too. There's a boundary phase transition where if I put enough fields on the boundary, I could feel the glass too. So is this part of it or not?
No, so in this metaphor of boundary is I'm trying to visualize the process of training.
Yes.
This process of training is, involved in changing the weights or changing the couplings. There is
Yes.
its own, it involves cost functions and all
Yes,
this.
well,
all
I
this
guess
stuff.
my question is
But-
very simple.
Yeah.
It's just that if I fix the J,
Yeah.
and I also put random fields on the boundary, I have a phase diagram with two parameters, which is the variance of the fields on the boundary and the variance of the J. There should also be a phase transition there.
Yeah, so I mean, I think you can do a lot of things with this.
Yeah.
That's kind of why.
This is not part of the story.
It's
yeah.
not, and you're welcome to explore it. I don't know why I would want to do that, but you can certainly do that. Yeah.
Well, on that note,
Yeah,
let's
right.
thank Victor.
Saying that we can reach the same point. We'll get the same economy. But if you just have a lot of that's if you give it all series,
Actually, the state of this is easy to look at. Yeah. That's second. Yeah, very much running in size. Yeah. So it's like T plus. Yeah. It's like top this out. Maybe yeah. Is it being excited if the people manage to look out like this, the manage to. So not everything can be all the way for that, making. Okay, it's I know this. It's not really, you guys, they do this. This is interesting. You need to observe them with the short various reasons, you know, flash. Yeah, so this one would be. Yeah, that one is the same. I think that's so I think that's maybe we'll have the same. But I think this is probably written. I could I'm that way. See the and I think there is saving. Just doing the 1 million dollars. Yeah. Well, exactly. If this was, if Cal was smaller, if you just had like one infield for that, that can. Or I mean, you can even do. Yeah, I think there might be a way to. Yeah. Pieces. And even if you evolve those. Evolving imagination wells. Yeah. Like it actually. Yeah. It could be like a we have one idea. You're going to be like just like in the version we need or after like the creative needs to be. I like this, like we haven't thought this serves you around for size your metal. Yeah. After that, then yeah, so then I that's like but then the thing that that is the that is and then just and then that's like taking sweet like involving it in another person. It works too okay. How is it? Again, it doesn't work too great. It's like small. Yeah, I mean, I think it would. I mean, it's still going to be but if this state was like very
I mean, it really depends on whether this state.
Yeah. I think it's the best idea. You're saying this is the volume so far. So these are kind of photos. Coming at it.
Yeah, it seems like. Let's say I started here and I go, well, it's like political, like that, this is a lot. And go back down and keep going.
Oh, yeah.
Down, keep going. And so it looks like the patterns is that down.
Exactly. Well, let's come back to the page.
But the thinking is, this is like, this is very similar to the experiment. Like, if I was doing something like PIG, I want to do a singular value definition. Well, then when I do that, I pull in some way. So these come from the environment, and these give me a picture on this page of relevant. But only then use that rotation, and then I apply something like this inverse. So in principle, I'm doing nothing, but I'm just applying. How will you use the finishing that? Doing an active project. But this just helps me get to choose and like this like this information.
Sort of like it's like saying API geometry for circle.